T-minus 10, 9, 8,
The clock is operating. We're underway.
Tranquility Base here.
Endeavour, go at throttle up.
Die Antennenschüssel besitzt einen Durchmesser von 300 Metern. In einen natürlichen Krater eingefügt, übertrifft sie die Leistung anderer Radioteleskope um das Dreifache. Die bewegliche Plattform über der Schüssel erfüllt gleichzeitig die Funktionen von Sender und Empfänger. Die Anlage von Arecibo arbeitet wie ein riesiges Strahlengeschütz, ausgerichtet auf Ziele, die Millionen Kilometer entfernt sind.
Wir können damit mehr entdecken als mit jedem anderen Teleskop auf der Erde. Heute Nacht geht es um einen Asteroiden, der etwa 5 Millionen Kilometer entfernt ist. Wir werden die genaue Distanz mit weniger als 10 Meter Toleranz ermitteln.
Das Teleskop sendet eine Serie starker Radarimpulse ins All. Ihr Ziel ist, von der Erde aus gesehen, nicht größer als ein Staubkorn. Eine halbe Minute später erreicht ein schwaches Echo die Asteroidenjäger. Der erste Kontakt ist hergestellt. Die Bilder auf Steve Ostrows Radarschirm gleichen Ultraschallaufnahmen. Schemenhaft enthüllen sie zugleich erstaunlich genau seine Details. Geographos besitzt einen Durchmesser von beinahe 5 Kilometern. Er besteht zum größten Teil aus Felsgestein. Andere Weltraumvagabunden sind Trümmer aus geschmolzenem Metall. Ostro erforscht erdnahe Asteroiden, deren Durchmesser von 30 Metern bis zu 24 Kilometern reichen. Das Radar liefert für jeden von ihnen exakte Daten über Größe und Geschwindigkeit. Millionen von ihnen existieren im All.
Jeder dieser erdnahen Asteroiden könnte die Bahn der Erde kreuzen. Vor einigen Jahrzehnten wussten wir noch nicht einmal von ihrer Existenz.
Vor 200 Jahren entdeckten Forscher in der süditalienischen Stadt Palermo zum ersten Mal einen Himmelskörper, dessen Erscheinung und Flugbahn ihn als einen Asteroiden auswiesen. Der englische Astronom David Hughes besucht den historischen Ort der aufsehenerregenden Entdeckung. Sein Ziel ist die alte Sternwarte auf dem Dach des königlichen Palastes. In ihrer Kuppel stellten Wissenschaftler das Verständnis des Sonnensystems auf eine neue Grundlage. Die technische Voraussetzung dazu war ein Teleskop, das bis heute unverändert den höchsten Stand der damaligen mechanischen und optischen Handwerkskunst zeigt.
Es ist ein Instrument von großer Präzision, eines der besten seiner Zeit. Und es ist schön. Die weiteste Reise lohnt, einfach nur, um es sich anzusehen.
Hightech des 19. Jahrhunderts, die der Erforschung des Himmels neue, atemberaubende Perspektiven eröffnete. Die Astronomen suchten damals nach einem fehlenden Planeten, den sie auf einer Bahn zwischen Mars und Jupiter vermuteten. Am 1. Januar des anbrechenden 19. Jahrhunderts entdeckt der italienische Astronom Giuseppe Piazzi einen neuen Himmelskörper. Der Zufall hilft ihm dabei. Er arbeitet an einer Sternentabelle und überprüft dafür die Position der Gestirne im Sternbild des Stiers. Piazzi hält seine Entdeckung zunächst für einen unbekannten Fixstern. Doch in der Nacht darauf hatte das Objekt seinen Standort gewechselt. Ein Fixstern kann es also nicht sein. Den ganzen nachfolgenden Monat scheint das Objekt wie ein Planet die Position auf einer Kreisbahn zu verändern. Piazzi gibt seine Entdeckung bekannt. Der fehlende Planet scheint gefunden. Er nennt ihn Ceres, nach der alten römischen Schutzgöttin Siziliens.
Ceres wurde am Himmel erwartet. Denn zwischen Jupiter und Mars ist in unserem Sonnensystem eine Lücke. Doch Ceres war nur ein Schemen, kein richtiger Planet. Und nach 1801 entdeckten Forscher weitere Trümmer in der Sternenlücke.
Piazzis Sensationsfund ist ein Asteroid. Mit 800 Kilometern Durchmesser gehört er zu jener schuttartigen Restmaterie, die bei der Geburt des Sonnensystems entstand. Die junge Sonne war eingebettet in eine wirbelnde Wolke aus Materie, eine riesige Scheibe aus Gas und Staub. Der Nebel ballte sich zusammen und bildete vermutlich die in ihrem inneren Gestein enthaltenen Planeten. Doch die Materie zwischen Mars und Jupiter verhielt sich anders. Die Konzentration blieb aus. Bruchstücke schwirren bis heute durch das Weltall.
Es gab genug Masse für einen Planeten, 4-mal größer als die Erde. Doch Jupiter hat die Materie abgelenkt. Statt Großes zu formen, wirbeln die einzelnen Teile durcheinander. Wir sehen heute einen großen Haufen von Bruchstücken in der Lücke zwischen Mars und Jupiter, den Asteroidengürtel.
Jenseits der Umlaufbahn des Mars, mehr als 160 Millionen Kilometer von der Erde entfernt, birgt der Asteroidengürtel tausende riesiger Himmelskörper, die in einem Meer kleinerer und kleinster Gesteinstrümmer treiben. Bis vor kurzem glaubten nur wenige Wissenschaftler, dass der Erde aus so großer Entfernung Gefahr durch Asteroiden drohen könnte. Doch dann begann der Mensch, den Weltraum genauer zu erforschen. Krater auf dem Mond galten ursprünglich als Reste erloschener Vulkane. In Wahrheit sind es Einschlagspuren von mehr als 300.000 Geschossen aus dem All.
Die Entfernung des Mondes von der Sonne ist der Erde ziemlich gleich. Wenn also der Mond von Asteroiden getroffen wurde, ist es der Erde mit Sicherheit genauso ergangen.
Immer wieder gefährden die gigantischen Gravitationskräfte des Jupiter die Stabilität des Asteroidengürtels. Gesteinstrümmer werden aus ihrer Bahn gerissen und in weite Umlaufbahnen um die Sonne geschleudert. So können sie auf Kollisionskurs mit anderen Gestirnen geraten. Einige von ihnen kommen der Erde gefährlich nahe. Near-Earth Asteroids haben die Forscher aufgeschreckt.
Asteroiden bewegen sich normalerweise auf einer Bahn zwischen Mars und Jupiter. Doch wenn Jupiter verrückt spielt, kann die Bahn auch so aussehen. Dann kommt der Asteroid der Sonne sehr viel näher. Und seine Bahn kreuzt hier die der Erde. Es besteht die Gefahr einer möglichen Kollision mit unserem Planeten.
Erosion und Vegetation haben fast alle Spuren verwischt. Doch die trockene Hitze Arizonas hat in der Wüste einen Krater perfekt erhalten. Er ist der Schlüssel für das Verständnis einer Kette von Katastrophen auf der Erde. Wie beim Mond galten Einschlagkrater auf der Erdoberfläche lange als Reste erloschener Vulkane. Vor etwa 50 Jahren gelang es Wissenschaftlern erstmals, eine der Geländenarben zweifelsfrei als Spur einer Katastrophe aus dem Weltall zu identifizieren. Der Geologe Jay Melosh hat das Puzzle zusammengefügt. Es zeigt, was geschah, als vor 50.000 Jahren ein kleiner Asteroid aus Metall mit kaum 36 Meter Durchmesser die Erdoberfläche traf.
Das Geschoss schlug hier auf, mit einer Geschwindigkeit von etwa 20 Kilometern in der Sekunde. Viel schneller als eine Gewehrkugel. Beim Aufprall zerplatzte es und explodierte.
Mit der Gewalt einer Atombombe von 20 Megatonnen schlug der Asteroid einen Krater in die Erdoberfläche, dessen Durchmesser 2000 Mal größer ist als sein eigener.
Nach der Explosion ging noch meilenweit vom Kraterrand entfernt ein Metallregen nieder.
Nur wenige Bruchstücke des Meteoriten aus Nickeleisen wurden geborgen. Doch verglichen mit anderen gleicht dieser Krater nur einem Nadelstich. Geologen konnten bisher über 150 große Einschlagstellen auf dem Erdball identifizieren. Das ist jedoch nur ein verschwindend kleiner Teil der tatsächlich vorhandenen Krater. Nach Schätzung der Forscher haben mehr als 3 Millionen Einschläge den Planeten erschüttert. Mit kriminalistischem Gespür gelingt es Wissenschaftlern, auch die verborgensten Spuren kosmischer Geschosse ans Licht zu fördern. Einige Kollisionen lösten gigantische Katastrophen aus, mit globalen Folgen. Sudbury ist ein wichtiger Industriestandort in Kanada. Seit mehr als 100 Jahren verdanken viele Einwohner ihren Wohlstand den reichen Nickelvorkommen der Region. Erst vor wenigen Jahrzehnten erkannten Wissenschaftler, dass die Stadt mitten in einem der größten Meteoritenkrater der Erde liegt. Er besitzt einen Durchmesser von über 200 Kilometern. Doch nur wenige Reste des Kraterwalls sind zu erkennen. Eindrucksvolle Felsformationen markieren den Verlauf.
Jetzt
Von Orten kosmischer Katastrophen auf der Erde.
schöner Einschlagskegel. Ich mache ein Foto. Die Schockwellen kamen von dort drüben und zerschmetterten den Felsen. Unter einem Mikroskop könnte man erkennen, dass die Oberfläche geschmolzen ist.
Die Einschlagskegel liefern den Beweis, dass das Areal ein alter Meteoritenkrater ist. Nur die ungeheure Wucht eines massiven Zusammenpralls konnte diese Gebilde formen.
Hier in Sudbury ist ein Asteroid von etwa 10 bis 20 Kilometern Durchmesser in die Erdoberfläche eingeschlagen und hat dabei die Erdkruste verändert. Sie reagierte nicht wie Fels, sondern eher wie Zahnpasta oder Wasser.
Das vollständige Ausmaß dessen, was sich vor fast 2 Milliarden Jahren bei Sudbury abspielte, ist unvorstellbar. Ein massiver Himmelskörper mit mehr als 15 Kilometern Durchmesser gerät auf Kollisionskurs zur Erde. Der gigantische Asteroid passiert den Mond mit einer Geschwindigkeit von mehr als 100.000 Kilometern in der Stunde. 3 Stunden braucht er noch, um die Erde zu erreichen. In nur 3 Sekunden durchschlägt das Geschoss aus dem All die Atmosphäre des Planeten. Fast 10 Kilometer tief bohrt sich die riesige Masse in die Erdkruste hinein. Die Wucht des Aufpralls schleudert unvorstellbare Mengen zerschmetterten Gesteins hoch in die Atmosphäre hinauf. Schockwellen jagen, begleitet von rasenden Winden, um die ganze Erde. Nichts vermag ihrem vernichtenden Druck standzuhalten. Ein Wall aus geborstenen Felsen und Sandmassen umschließt den Einschlagskrater. Er erreicht eine Höhe von über 1,5 Kilometern. Geschmolzene Lava dringt durch die Erdkruste nach oben. Erdbeben erschüttern den Planeten bis in sein tiefstes Inneres. Vom Himmel regnen Millionen Tonnen Gestein auf die Erde zurück und füllen den Krater zu einem flachen Plateau auf. Experten gehen davon aus, ein Zusammenstoß von gleichem vernichtenden Ausmaß könnte sich jederzeit wiederholen. Die Wahrscheinlichkeit ist allerdings gering, doch wenn es geschieht, sind die Auswirkungen für die Menschen verheerend. Die Sternwarten rund um die Erde sind seit langem in Alarmbereitschaft. Sie halten ständig Ausschau nach Objekten am Himmel, die dem blauen Planeten Erde gefährlich werden können. Nach neuesten Erkenntnissen stellen weniger als 1000 größere Asteroiden aufgrund ihrer Umlaufbahn eine Gefahr für die Erde dar. Doch es gibt mehr als 100.000 weitere von der Größe eines Fußballfeldes und 100 Millionen mit den Maßen von Wohnhäusern. Könnten alle Asteroiden optisch erfasst werden, die groß genug sind, eine Stadt auszulöschen, sie übertreffen die Zahl der heute am Himmel sichtbaren Sterne bei weitem. Welche Möglichkeiten bestehen, einen Himmelskörper auf Kollisionskurs mit der Erde von seinem Ziel abzubringen? Ein international abgestimmter Krisenplan, um die Menschen vor einer solchen Gefahr aus dem All zu schützen, fehlt zurzeit. Doch einzelne Wissenschaftler haben sich darüber ihre Gedanken gemacht.
Die Erde vor einer Kollision mit einem Asteroiden zu schützen, ist nicht so einfach, wie es scheint. Die meisten kommen erst einmal auf die Idee, ihn mit einer Atomwaffe zu sprengen. Das Problem ist nur, die Teile sind radioaktiv verseucht und setzen ihre Bahn ungehindert fort.
Ein besserer Plan, den anfliegenden Himmelskörper aus seinem Kurs zu zwingen, könnte der Beschuss mit Raketen sein, um das Objekt in eine neue Richtung zu stoßen. Ein anderer Weg wäre, ihn ins Schlepptau riesiger Sonnensegel zu nehmen, die ihre Energie durch das Licht des Zentralgestirns erhalten. Jay Melosh hat dazu eine eigene, bemerkenswerte Idee.
Man könnte die Sonnenenergie auch bündeln und auf den Asteroiden richten, sodass er beginnt, sich aufzulösen. Auf die Veränderung würde der kosmische Vagabund mit der Zeit reagieren und so allmählich aus seiner Bahn gelenkt.
Ein riesiger Hohlspiegel im All könnte die Energie der Sonne auf den Brocken konzentrieren. Auch ein anderer Vorschlag von Melosh könnte eines Tages in den Bereich des Möglichen rücken.
Angenommen, der Fels, auf dem ich sitze, ist der Asteroid. Ein Weg, ihn zu bewegen, ist, dass ich einen Stein aufhebe und ihn fortschleudere. Der Rückstoß treibt mich ein wenig in die dem Wurf entgegengesetzte Richtung. Dann werfe ich einen zweiten Stein. Das gibt einen weiteren Impuls. Indem ich also einen Stein nach dem anderen werfe, dränge ich den Asteroiden aus dem Kollisionskurs mit der Erde heraus.
Rock after rock, I can drive my asteroid out of collision course with the Earth.
Noch ist das alles Zukunftsmusik, doch die Zukunft hat bereits begonnen. 1996 startete eine Weltraumsonde zu einer aufsehenerregenden Mission. Mit hochauflösenden Kameras bestückt, sollte sie Bilder aus Bereichen des Alls übermitteln, in die bisher noch keines Menschen Auge Einblick nehmen konnte. 5 Jahre später, Februar 2001, erreicht die Reise ihren ungeplanten Höhepunkt. Eine Begegnung im All entwickelt sich für die Raumforschung zum wichtigsten Meilenstein seit der Landung auf dem Mond. Bob Farquhar wagt als Projektleiter, was zuvor kaum jemand für möglich gehalten hatte.
Menschen auf einen erdnahen Asteroiden zu schicken, ist leichter als eine Mondlandung. Die Entfernung ist zwar größer, doch weil jede Schwerkraft fehlt, ist die Landung einfach.
Bob Farquhar leitet ein NASA-Projekt, das zum Ziel hat, möglichst kostengünstig Asteroiden und Kometen zu erforschen. Für die Reise zum Rendezvous mit einem Asteroiden muss Farquhar der Sonde zunächst durch eine Reihe genau berechneter, schleifenförmiger Erdumrundungen die nötige Beschleunigung verleihen. Das Ziel heißt Eros, ein unregelmäßiger Himmelskörper von etwa 44 Kilometer Länge. Die Forscher wissen wenig über den Asteroiden. Sie kennen nur die Bilder, die das Radargerät liefert. Im Februar 2001 gelingt es den Wissenschaftlern, die Sonde in eine Umlaufbahn um Eros zu lenken. Ein ganzes Jahr hindurch liefern ihre Kameras über 1 Million gestochen scharfer Bilder von der Oberfläche des geheimnisvollen Objekts. Am Ende der erfolgreich abgeschlossenen Mission fasst Farquhar einen kühnen Gedanken. Er will einen Schritt weiter gehen und auf Eros landen.
Wir hatten die Gelegenheit zu wagen, was noch keiner zuvor getan hatte. Wir wären verrückt gewesen, wenn wir es nicht gemacht hätten.
Die Forscher planen ein Manöver, für das ihre Raumsonde gar nicht konstruiert ist. Sie besitzt kein Landegestell und der Treibstoff geht zu Ende. Doch zumindest besteht die Chance auf weitere sensationelle Fotos beim Abstieg.
Weil wir Fotos machen wollten, mussten wir mit den Kameras voranlanden. Die Antenne zur Erde und die Sonnensegel zur Sonne ausgerichtet. Wir mussten 3 Dinge auf einmal tun.
Am 12. Februar 2001 um 18 Uhr beginnt der Abstieg der Sonde aus ihrer Umlaufbahn. Auf dem Weg zur Oberfläche von Eros entstehen 69 Bilder. Die ersten, die einen der geheimnisvollen Himmelsvagabunden aus so großer Nähe zeigen. Zwei Stunden dauert es, bis die letzten Meter vor dem Boden erreicht sind. Dann gelingt Farquhars Team das schier Unmögliche. Die sanfteste, automatisch gesteuerte Landung in der Geschichte der Raumfahrt. Von Eros droht der Erde keine Gefahr, doch es existieren Millionen anderer Himmelskörper, deren Bahn unbekannt ist. Die Atmosphäre des blauen Planeten ist einem ständigen Bombardement kleiner und kleinster Meteoriten ausgesetzt. Die meisten verglühen in der schützenden Hülle der Erde. Manche zerbersten beim Eintritt in die Atmosphäre, wie hier über Langley im amerikanischen Bundesstaat Virginia. Ein Amateurvideo hält 1972 einen großen Meteoriten über den Rocky Mountains fest. Er schrammt die Schutzhülle der Erde und prallt zurück ins Weltall. Hätte er die Erde erreicht, wäre vielleicht eine Stadt ausgelöscht worden. Tunguska in Sibirien. 1908 ereignet sich ein Zwischenfall, der eindrucksvoll die Gefahr aus dem Universum belegt. Ein Objekt mit einem Durchmesser von 60 Metern explodiert über der Erde und verwüstet fast 2000 Quadratkilometer im Umkreis. Ausgelöst wurde die Katastrophe vermutlich durch einen erdnahen Asteroiden oder einen Kometen. Anders als Asteroiden bestehen Kometen in der Hauptsache aus Eis und Staub. Ihr Auftreten ist spektakulär. Stets ziehen sie einen leuchtenden Schweif aus Gas hinter sich her. Die jüngsten Besuche dieser Art aus dem All waren die der Kometen Hyakutake im Jahr 1996 und Hale-Bopp 1997. Historische Quellen belegen, die Erscheinung eines Kometen versetzte die Menschheit seit jeher immer wieder in Angst und Schrecken. Im 17. Jahrhundert stellt Edmund Halley fest, dass die geschweiften Unheilsboten Teil des Sonnensystems sind, indem sie weite elliptische Umlaufbahnen um das Zentralgestirn beschreiben. Halley berechnete die Bahn des heute nach ihm benannten Kometen genau und erkannte, dass er die Sonne alle 76 Jahre passiert. Die wohl berühmteste historische Quelle für sein Auftreten ist die Darstellung des Kometen auf dem Teppich von Bayeux von 1066. Sein vorerst letzter Besuch findet 1986 statt. Das Erscheinen wird erwartet und die Teleskope aller Sternwarten der Welt richten sich auf ihn. Die europäische Raumsonde Giotto nähert sich dem Kern des Kometen auf 650 Kilometer und liefert erste aufsehenerregende Bilder.
Die Europäer schickten dem Kometen die Giotto-Mission entgegen. Ich war damals im Kamerateam. Und so gehöre ich zu denen, die die ersten Bilder eines Kometenkerns aufgenommen haben. Kometen sind Urmaterie. Wir sehen etwas vor uns, das seit 4.500 Millionen Jahren tief gefroren ist.
Kometen sind, wie Asteroiden, Trümmer aus der Entstehungszeit des Sonnensystems. Die neugeborenen Planeten entwickeln gewaltige Gravitationskräfte. Sie schleudern in einem Hagelsturm gefrorenen Eisstaub nach außen fort. Weit jenseits des Sonnensystems breitet er sich aus als ein unermesslich weites, eisiges Staubmeer. Es ist die Oortsche Wolke. Sie umschließt die Sonne und alle Planeten. Auf ihrer Umlaufbahn um das Zentralgestirn durchquert die Erde auch den Schweif mehrerer Kometen. Immer wieder glühen Staubteilchen auf, wenn sie in die Erdatmosphäre eintreten. Doch nicht alle Kometensplitter verbrennen. Viele Partikel überstehen den Sturz durch die Lufthülle und gelangen auf den Boden. Tausende von Tonnen kosmischen Staubs erreichen so jedes Jahr die Erde. Menschen berühren ihn, nehmen ihn mit dem Essen zu sich und atmen ihn ein, Tag für Tag. Und es scheint, dass kosmischer Staub vielleicht in der Frühzeit der Erde eine wichtige Rolle bei der Entstehung des Lebens spielte. Der blaue Planet entstand vor etwa 4,5 Milliarden Jahren. In den darauffolgenden Jahrmillionen war er, ebenso wie der Mond, einem ständigen Bombardement aus dem Weltall ausgesetzt. Auf der Erde tobte in ihren Jugendjahren eine wahre Hölle. Die empfindlichen Grundstoffe des Lebens konnten nicht bestehen. London. Am Naturgeschichtlichen Museum vertreten Wissenschaftler eine revolutionäre These. Sie wollen beweisen, dass das Leben auf der Erde von außen auf den Planeten gebracht wurde. Matthew Jenschs Spezialgebiet ist die Erforschung von kosmischem Staub.
Staub aus dem Kosmos kann den Sturz durch die Atmosphäre überstehen. Was am langsamsten fällt, gelangt auf den Erdboden, wo wir es finden und untersuchen können.
Jensch sucht die Staubpartikel da, wo die Natur sie am besten konserviert, auf den Eisfeldern der Antarktis. Nahe dem Südpol finden Wissenschaftler die oft winzig kleinen Botschafter aus dem Sonnensystem.
Die Antarktis ist sehr sauber. Vom Pol her wehen starke Winde. Wenn wir das Eis schmelzen, finden wir unter den Staubteilchen viele, die eindeutig aus dem Weltall stammen.
Unter dem Elektronenmikroskop gewinnt der Forscher Einblick in die Struktur der winzigen Objekte in 200.000-facher Vergrößerung. Jensch kann ihre Geschichte um Milliarden Jahre zurückverfolgen.
Über die winzigen Erhitzungsspuren vom Sturz durch die Atmosphäre kann ich viele außerirdischem Ursprung zuordnen. Dies Teilchen zeigt abgerundete Formen. Sie entstanden durch Gasentwicklung in seinem Innern.
Jensch erkannte, dass viele der Staubkörner Kohlenstoffverbindungen enthalten. Sie sind das Rohmaterial für die Entwicklung von Leben. In jüngster Zeit wurden Missionen auf den Weg ins All gebracht, um dort Gesteinsproben direkt aus dem Schweif eines der Raumvagabunden zu gewinnen. Im Jahr 2004 soll die NASA-Sonde Stardust den Kometen Welt 2 erreichen. Stardust ist speziell für die Aufgabe entwickelt worden, kosmischen Staub einzufangen. Das gesammelte Material soll anschließend zur Erde gebracht und dort analysiert werden. Doch ein Geheimnis bleibt. Wenn kosmischer Staub die Grundelemente des Lebens zur Erde brachte, wo und wie konnten sie im Höllenfeuer auf der Oberfläche des jungen Planeten bestehen? Immer neue Kollisionen mit Asteroiden und fortwährender Strahlenbeschuss hielten das Inferno ständig in Bewegung. Wissenschaftlern ist es bisher nicht gelungen herauszufinden, wie unter solchen Bedingungen die ersten lebenden Organismen entstanden. An den Felshängen des Einschlagskraters von Sudbury sucht David Kring nach Hinweisen. Im Gestein könnte sich der Schlüssel zum Geburtsort des Lebens verbergen. Kring nimmt die Spuren einer weit zurückliegenden Katastrophe auf.
Die Explosionshitze brachte Wasser und andere flüssige Stoffe innerhalb der Erdkruste in Bewegung. Dieses System von Austausch und Bewegung bildet das Laboratorium der Ursprungschemie, aus dem einfachste Lebensformen hervorgehen konnten.
Verborgene Spalten tief in der Erdkruste schützen die Geburtsstätte des Lebens vor Strahlungen und ständig neuer Verwüstung aus dem All.
In dieser Gesteinsprobe vom Grund des Kraters in Sudbury erkennt man eine Ader, in der Flüssigkeit transportiert wurde. Das hydrothermische System im Gestein könnte vielleicht 1 Million Jahre bestanden haben. Genug Gelegenheit für die Weichenstellung zur Entwicklung von Leben.
Ein schwerer Asteroideneinschlag erschütterte die Erde vor 65 Millionen Jahren bei Xixcoulub im Golf von Mexiko. Feuer stürzt vom Himmel. Milliarden Tonnen von Felsen und Staub wirbeln in die Atmosphäre. Sie verteilen sich in einer riesigen Wolke wie eine Hülle um den ganzen Erdball. Wenige Stunden später geht dichter Gesteinsregen auf das Antlitz des Planeten nieder. Feuerstürme rasen um die Erde. Die gesamte Vegetation fällt den wütenden Flammen zum Opfer. Die Oberflächentemperatur steigt um viele 100 Grad. Rauchwolken mischen sich mit Asche und halten auf Jahre das Sonnenlicht von der Erde fern. Als Folge davon beginnt die Temperatur zu sinken. Nur wenige Arten von Lebewesen sind dem kosmischen Wintereinbruch gewachsen und überleben. Die Evolution ändert ihren Verlauf. Die Kollision ist kein Einzelfall. Die Entwicklungsgeschichte belegt weitere überraschende Richtungswechsel.
Katastrophen in der Größenordnung von Sudbury oder Xixcoulub ereignen sich etwa alle 100 Millionen Jahre. Seit Leben existiert, müsste es 5 oder 6 gegeben haben.
Fossile Überreste ausgestorbener Tierarten helfen, Massensterben der letzten 500 Millionen Jahre zu datieren. Wenn es den Geologen gelingt, einen zeitlichen Zusammenhang zwischen kosmischen Katastrophen und Artensterben zu belegen, würde vermutlich deutlich werden, dass Asteroiden in der Entwicklung des Lebens eine zentrale Rolle spielen.
Der Chicxulub-Asteroid beendete das Zeitalter der Dinosaurier und das der Säugetiere begann. Vermutlich hat er damit auch die Entwicklung der Menschen begünstigt.
65 Millionen Jahre sind seit der letzten großen Kollision mit einem Himmelskörper vergangen. Doch jederzeit kann sich ein ähnliches Ereignis wiederholen. Von Arecibo helfen, Gefahr aus dem All zu erkennen. Ihre Teleskope erforschen den Himmel auch, um mehr über die unheimlichen Besucher aus dem All zu erfahren. Nur mit Hilfe des Radars können sie ihre Größe und Flugbahn feststellen. Der Asteroidenjäger Steve Ostrow hofft auf seine erste Kontaktaufnahme mit einer neuen Welt, dem Asteroiden KW4.
Wir peilen ihn an und eine halbe Minute später empfangen wir das erste Echo. Im Wechsel zwischen Senden und Empfangen erhalten wir ein genaues Bild von ihm.
5 Minuten nach Mitternacht erreicht Steve Ostrow und seine Männer das erste Echo. Mit großer Spannung entschlüsseln sie die Signale. Um 2 Uhr erscheint das erste schemenhafte Bild von KW4 auf dem Monitor.
Es ist ein großes Objekt, das sich sehr schnell um die eigene Achse dreht. Und da ist noch ein zweites Objekt, kleiner und nicht so schnell drehend. Sie umkreisen sich, ein Doppelobjekt, das ist auffällig.
Steve Ostrow hat 2 neue Welten entdeckt. Die große hat einen Durchmesser von 1200 Metern. Sie liegt etwa 4,5 Millionen Kilometer von der Erde entfernt, nur 12-mal weiter als der Mond.
Wir haben etwas auf dem Monitor. Das ist ein bewegender Moment und ein folgenschwerer. Wir wissen, dass diese Objekte für die weitere Zukunft der Menschen eine wichtige Rolle spielen werden.
Es gibt bereits Wissenschaftler, die Asteroiden völlig neue Funktionen beimessen. Sie spielen mit dem Gedanken, die Himmelskörper als Sprungbrett zu nutzen für den Aufbruch des Menschen zu den Sternen. Kolonien von Robotern könnten ausgesetzt werden, um Bodenschätze zu gewinnen. Selbst menschliche Siedlungen werden denkbar. Steve Ostrow ist sicher, dass sich einige der neu entdeckten Objekte durchaus für die Kolonisation eignen.
Es existieren viele Gründe, die für eine Besiedlungspolitik sprechen. Zum Beispiel die Gewinnung von Bodenschätzen. Das Vorkommen von Wasser ist der Schlüssel solcher Star Trek-Fantasien, von Menschen, die ständig im All leben. Die Reise auf einem Asteroiden durch das All könnte Kolonisten auf fantastischen Bahnen durch das Sonnensystem führen. Es sind Millionen verschiedener Möglichkeiten, die darauf warten, von uns entdeckt zu werden. Und irgendwo befindet sich manchmal ein Objekt auf Kollisionskurs zur Erde. Nur, wir wissen nicht, wann es sich zeigt.
Wenn es gelingt, einen Asteroiden oder einen Kometen zu entdecken, von dem der Erde Gefahr droht, brauchen wir einen Plan. Wie sollen wir der drohenden kosmischen Katastrophe begegnen? Wenn ein großer Asteroid Kurs auf die Erde nimmt, werden wir nur einen Versuch haben, uns zu verteidigen.
The thing that's really cool about this mission is there's nothing subtle about deep impact. It's something that anyone can understand. We're trying to smack a comet as hard as we can with a hunk of copper. We'll be going about 23,000 miles per hour, and we're going to watch what happens. And we actually get a surprising amount of excellent science data from this impact. We don't know what the interior of a comet is composed of. We don't know whether it's densely packed or loose, and we're going to learn a lot about that from this impact.
This is a first of a kind, and it's really exciting because what we're trying to do is not only hit the comet with an impactor spacecraft, but to also have a second spacecraft watching and seeing the impact at the same time. and taking the pictures of the crater formation and getting the science data that's really behind this mission. So we like to equate that to a bullet hitting a bullet and another bullet trying to look at the same spot at the same time. This particular comet is from what we call the Kuiper Belt, and so it has a periodicity of about 5 years, so once every 5 years it comes into the inner solar system. These are what they call the periodic comets. It's not overly active where you see a lot of the jets, which we don't want to go to because we don't want one that's overly active. So it's just about the right size of activity for us to be able to perform this mission. We expect that deep impact will create a crater that will throw this dust up into the sunlight so we can actually get the pictures and the spectra of what that dust and material and that debris coming out of the crater actually is. Based on the cratering, when we actually smack this thing at 23,000 miles an hour, is you will get the basic properties of the comet and be able to apply that for future knowledge. You would be able to use that knowledge to understand how much and with what you got to hit one of those things to knock it off course. Now, this will not knock this comet off course, and it'll be like a gnat hitting a 747 airline.
Deep Impact is a remarkably quick mission as deep space missions go. It's only 6 months in duration. It's been a very intense period. We've got a great team on Deep Impact, and it's a very diverse group of people. And we've got people from the Jet Propulsion Laboratory as well as Ball Aerospace operating simultaneously from 2 different sites. We've got a lot of work to do, but we've got a great team to get it done.
Well, if you've been looking at Mission Control, you'll notice that you see red shirts and blue shirts, and the person here with me right now can explain that to us. You're wearing a blue shirt, though.
That's right. We've given blue shirts to all the people that are supporting the flyby spacecraft and the management at the back of the room. The people in the red shirts are the impactor folks.
All right. Well, let me introduce this guy. This is Dave Spencer. He is the mission manager for Deep Impact. Dave, go ahead and give us just some background. Bring us up to speed on what's happened thus far.
Well, we've reached a very exciting point in the mission. Obviously, we're in the climax right now, and just here in the last few minutes, we've gotten within the last 2 hours prior to impact, and so we're now processing AutoNav images, and AutoNav, for the first time on the impactor, is computing a solution, trying to figure out exactly where to target to on the surface of the comet.
What's amazing about this mission is that we've only been operating the spacecraft for 6 months. And we have actual video of launch day,
right? And
that was just in January. That's amazing.
Yeah, it seems like a long time ago at this point. We've really been working at breakneck speed, and thinking back to January, it seems like a lifetime ago. But here, let's look at the video here. So this was launched back on January 12th, picture perfect day, and we had a spectacular launch. Everything went just great, and we were ecstatic to have a healthy spacecraft up in space. So we had a 6-month cruise to get to Temple 1, which is short by planetary mission standards. The spacecraft performed just wonderfully. Temple 1 comes in from out around the orbit of Jupiter, and it's nearing the closest point to the Sun called the perihelion. Here shows impactor release. That occurred just last night. Everything went just perfectly, much better than we had tested, in fact. Things went very smoothly, and our navigation team basically delivered a bullseye. The latest orbit determination shows that the impactor is within 2 kilometers of what we think is the center of the target, center of the comet. And so the impactor AutoNav system it still has to work, but it doesn't have to work quite as hard as what we thought it might.
So
that's excellent.
The last big nail-biting moment last night was separation. What was that like here?
Well, we had separation and divert last night. So the separation event, we were looking at the Doppler shift, basically the radio signal that comes back from the flyby spacecraft, and you can see the characteristic knee in the curve when the impactor separated from the flyby and gave a nudge to the flyby spacecraft. It's a great feeling. I mean, we've worked towards this for a long time, and it was one of the big risk items left in the mission. It was great to see that risk behind us.
We have video of that event right now.
Copy, thank you.
So just after separation, we went into the divert maneuver, and that was a 100 meter per second burn, slowed this flyby spacecraft down by 220 miles per hour. So I guess this here is last night.
And things went actually better than expected?
Well, we've actually done 4, we call them operational readiness tests, or effectively dress rehearsals that we've run through just to make sure that we've got everything ironed out. And there are always little glitches. It's actually harder running these things oftentimes on the test bed on the ground than it is to work with your spacecraft in flight. And last night, everything went just picture perfect. We did have a little bit of nail-biting time. Here's Larry Murphy, and you see when he reacted like that, that's when we got the radio signal back from the impactor spacecraft and basically knew that the impactor was okay after separation. So that occurred just a few seconds later than what we thought it would, and so, you know, it added to the intensity of the moment a bit.
All right, so we have separation. What else could be in store for us?
Well, these last 2 hours are very critical. You know, we're vulnerable to some things that Mother Nature could throw at us, like cosmic rays, like solar flares. Those sorts of things it would be very difficult to recover from. And crews, when we've got time to recover, we can you know, get commands up and get back in action. But in the last 2 hours, there's very little we can do here. So we're just riding it out at this point.
And every so often you hear the engineers talk about the knuckleball. What do we mean by that?
Well, comets, they're pretty difficult targets to hit. You know, I mentioned that the comet's approaching its nearest point to the sun. As it gets closer to the sun, it becomes more active. And it starts outgassing material from the surface. And every time it does that, the orbit moves a little bit. And I liken it to a baseball player trying to hit a knuckleball. It's a pretty difficult target to hit, but our navigation team's done a fantastic job and put us on a course for an impact.
All right. Well, there you have it. You have it from the mission manager himself, Dave Spencer.
Well, we've had several spacecraft fly by comets and take pictures as they went quickly past. The first was the Giotto spacecraft back in March of 1986, and we had the Deep Space One spacecraft fly quickly past Comet Borrelly. The Stardust spacecraft flew quickly past Comet Wilt 2 and picked up some dust samples to bring back to Earth. But as they're all quick flybys, so you have to take pictures as you go by very quickly, so you don't get a chance to study the comet, and you certainly don't get a chance to understand what's in the inside of a cometary nucleus. And that's, of course, what the primary science goal for the Deep Impact mission is. What is a comet made of? How is it put together?
The impactor for Deep Impact is a fully functional spacecraft. It's not just a cannonball. It's got a camera on it. It has a propulsion system, attitude control system, spacecraft computers, all those things that you traditionally think of as part of a spacecraft. If you were riding on the impactor, you're approaching the nucleus at 10 kilometers per second, or a little over 6 miles per second. Ultimately, half of the impactor mass is copper, and that corresponds to approximately 45,000 pennies. We have a prediction that we will excavate a crater the size of a football stadium in about 200 seconds. However, the research community disagrees on the nature of comets. They disagree on how they're held together, and they therefore disagree on what the cratering process will do, and therefore on what kind of a crater we'll get at the end.
Well, there's a couple of scenarios that could play out when the impact occurs. If the comet is solid, like a solid ice ball, like a block of ice you might take out of your refrigerator and put in your drink, if it's that hard, then the crater will be relatively small, just 10, 20 meters in size, and it will form rather quickly. On the other hand, if it's a fragile object, sort of like a souffle or the foam on a cappuccino or something like that, we're expecting a much larger crater, and it's going to form more slowly over a few minutes. But either way, we're going to know how the comet is put together. comets are not only important for understanding how the outer solar system formed and how life, the ingredients of life were brought to Earth, but they may well be important for future space exploration. In the coming decades, when we start to send manned spacecraft out into the inner solar system, we're going to need water, and comets are about half water ice to survive, and we're going to need rocket fuel. And comets, of course, water is hydrogen and oxygen. And if you can break the water down into hydrogen and oxygen, that is the most efficient kind of rocket fuel. So in the future, comets may well be the watering holes and the fueling stations for interplanetary travel.
With me now is one of the faces you saw in that science package, Mike Ahern, Dr. Mike Ahern with the University of Maryland, and also the principal investigator of this project. Mike, first of all, just fill us in. There have been comet missions before. What makes this one different?
The real difference between this mission and the other missions is that we're looking at the differences between the surface and the interior of the nucleus. A lot of other missions have looked at the surface, but nobody else has looked inside before, and that's the whole goal.
And the science underneath. Can you explain the key of the organics that you're looking for?
Right. We want to find out really what the early solar system was like, and to do that, we need to look at the material that's been preserved from 4.5 billion years ago, and we think that lies in the interior of the comets. Both ices and organic materials, all of the materials that provided everything you needed to have life on Earth when comets and perhaps some asteroids brought all those volatiles and organics to Earth roughly 4 billion years ago.
Now, we actually have an image of Temple 1, an image from the impactor after it was released. Let's go ahead and take a look at that picture. The question is, why Temple 1? Why this comet?
Well, this comet, which is right now roughly what you would see if you were riding on the impactor, was chosen largely because it was in the right place at the right time. We could design a mission that would approach it from the sunward side instead of from the dark side, and we could get there with a lot of energy very easily with an affordable launch vehicle.
So I imagine this is a very exciting moment for you. This is a culmination of a lot of work.
Absolutely.
All right. Good luck to you. And we will hear more from you later on this evening. All right. Dr. Mike Ahern, Principal Investigator of Deep Impact.
Unter Beschuss. Die US-Weltraumbehörde NASA hat im All eine Sonde ausgesetzt, die heute früh auf den Kometen Tempel 1 einschlagen soll. Das kühlschrankgroße Objekt soll einen Krater so groß wie ein Fußballstadion in den Himmelskörper sprengen. So will die NASA erstmals den Kern eines Kometen erforschen.
We still haven't had confirmation that we have impact. That will come a little bit later. We'll first have to lose the S-band signal, and then we're going to have confirmation from all of the images.
More peanuts, please.
Grunde. Wissen Sie, ist das schon so, dass man wirklich nicht wusste, was da kommen würde?
Wir wissen das jetzt noch nicht. Wir haben ja jetzt den Impact noch nicht gesehen. Das ist ja der entscheidende Punkt, ist, dass wir sehen, wie sieht der Krater aus, wie fliegen die Teilchen weg nach dem Einschlag. Da lernt man ja wirklich was über die Konsistenz, über die Zusammensetzung des Kometen an der Oberfläche oder des Kometen selber und auch dann nachher chemisch, die chemische Zusammensetzung. Das sind Bilder von einer vielleicht besseren Qualität, als wir sie bereits haben von
aber
anderen
jetzt
Kometen.
sehen wir Jubel.
Offensichtlich ist das der Einschlag. hat man den Anschlag irgendwo gesehen.
Das heißt, ab jetzt wissen die Wissenschaftler in Pasadena, dass es ein Erfolg war. So sieht's aus.
Ja.
Mal gucken, ob wir noch mehr erfahren können. Vielleicht können wir da mal reinhören.
Put that up on the screen.
Without hearing...
There is an incredible image you have to put up on the screen.
Oh, that's got to go up on the screen.
The impact. I mean, you got to get it up there.
Without hearing official confirmation from NASA, this is pretty close to the actual thing here, seeing all the high fives going around the JPL control room, reminiscent of what happened with the Mars rovers not too long ago.
You got to put that image up.
The impact took place. There's clearly no real clarity as to when we're actually going to get these pictures. Why is it so uncertain as to how long it's going to take to get those pictures back to NASA?
Well, there are a lot of variables in place. Some amazing pictures you can see right here. Depending on how good the resolution is, the interference out in space, getting back down into the Earth's deep space network and analyzing the pictures. But clearly, the scientists here at NASA and JPL are very excited about what they've got so far. There will also be pictures from the orbiting telescopes, the Hubble, the Spitzer, all the ground-based orbiting systems, ground-based telescopes and so on, trying to get pictures of all this, and the orbiting systems as well. There's a whole library of data that's going to come together for this project. It's going to be spread out over the next coming days and weeks to analyze all of this. But clearly, the scientists...
That's going to take a long time, isn't it?
It could take a while to process all
that is really going to take a lot.
We have final confirmation.
And I think we're hearing final confirmation that the impact did occur as NASA had planned. And hard to know exactly when it occurred, but for a mission that's taken this long, to get it down to a couple minutes.
Folks here are looking at the images, and they are indeed amazing images.
There's nothing subtle about that one.
Flyby ACS. Go ahead. All right. Yeah, we're well into the encounter slew now. We're up to 250 microradians per second climbing. Copy.
So those would be the impact images,
that image
Charles.
Says it all. We hit it just exactly where we wanted to. And we're going to get additional images.
You're hearing them say they hit it exactly where they wanted to.
Another 13 minutes before we go into shield mode. And that's where we get our highest resolution images from the flyby spacecraft. But oh, look at that image. If that doesn't make the front page, there's something very wrong.
There we're seeing some images from the actual impact itself.
Look at that.
And the key to all of this, again,
Daniel,
is
I'm to be subtle.
Charles?
I thought, oh my Lord.
Daniel, just to update viewers, and we welcome viewers of CNN USA along with viewers on CNN International, and we are at the NASA Space Propulsion Laboratory there looking at live pictures, or almost live pictures, coming back from the impact that has been engineered by those NASA scientists between a space probe and a comet, which is going to allow us to analyze for the first time material from inside that comet. And I'm joined now by Daniel Seberg, who is the CNN technology correspondent. Daniel, again, this looks like an extraordinarily successful operation, at least so far, right?
Incredibly successful and some amazing pictures. What you're seeing right there on the screen right now, the impact pictures from the flyby spacecraft, which happened just minutes ago. And really, this is the important part of the science. What you're seeing here is this explosion, about 5 tons of TNT exploding out of this comet as the probe hits it. And you can see there it's illuminated by the sunlight. That is key to getting information from the actual event so that scientists can process it and get a better understanding of what makes up a comet, what the ingredients are for a comet, because really they are like a time capsule out in space. And what scientists are hoping to discover is what formed them. It would have a lot to do with what the solar system went through about 4.5 billion years ago when it was formed. And so this is essential data, and that is an amazing picture. And you can see the reaction earlier from some of the scientists on the ground at the Jet Propulsion Lab in California reacting to this. This has been planned for several years. And to get down to these pictures, this is exactly what they were hoping to get. And obviously very elated. You're seeing some more of these pictures come in now live at JPL in California.
About 30 minutes from now, and we just like all the information you have as far as reconstruction and performance from each subsystem.
Daniel, one thing that I find very interesting talking to experts about this is they didn't even really know what the impact would be like. Whether this thing, which weighs about 800 pounds, 372 kilos, would blast an enormous hole in the comet about the size of a football stadium, or whether it would just blast a hole about the size of a room, despite the fact that the impact would be at about 40,000 kilometers an hour. That's 23,000 miles per hour. I mean, this is the extent to which we really don't know what the comets are like inside, right?
Exactly. I mean, this is really a big mystery for scientists. What does make up a comet? They have never attempted anything like this before, and to get inside a comet like this is really new territory for these scientists. And to be able to go this distance, 268 million miles, it's about 83 million miles from Earth. It's not exactly a straight line. The flight path of the actual deep impact wasn't a straight line, but it's about 83 million miles from here. And when they actually process all of this data, it could really provide some amazing insight into how the solar system formed. It really was like sending a washing machine into space to hit this. Now, of course, they had some control over it when it got there, but the NASA officials have described this as one bullet hitting another bullet with another bullet flying by to get pictures of it. So they've been threading the needle in a sense with this mission, and obviously it's paid off for them, and you can see the elation and the excitement at NASA over having, for what we can see, succeeded in this mission.
Just to take a step back, how long has this mission been underway? When was this conceived? Because the launch was actually only at the start of this year of the probe that was fired off, right?
Right. The launch itself to get the probe and the mothership up into space was in January of this year. But the mission itself has been conceived of for several years, and to get it into this place, an enormous amount of work has been done, tireless hours and coordination to get all of the things in place to make this happen. It took 6 months just to get the flyby spacecraft and the impactor in position. Really what we're talking about here is a jetliner. This is an enormous comet, if you can get the idea. It's half the size of the island of Manhattan in New York. So it's really like a jetliner hitting a mosquito. That's the way that they described it. They put the impactor in the path of this comet. The comet hit it. It created this enormous impact, or this explosion in a sense, on the surface of the comet and into the comet. And you can see there some of the pictures from the flyby spacecraft that captured this as it happened. It only had a limited number of seconds, really, about 800 seconds worth, to grab these images as it was going by. Remember, we're talking enormous speeds here, 23,000 miles per second. That is an incredible, 20,000 miles per hour, I should say. That is an enormous rate of speed to try and make all of this happen at the right time and coordinate all of this from the ground. And really an amazing event for NASA.
Daniel, let's remind ourselves, this is an enormous lump of matter. We don't think that it has life on it. We'd probably treat it very differently if we did. But what is the fascination of comets? What is the difference between comets and planets? Why would a comet be of any interest when we're already starting to touch the planets?
Well, comets are just so mysterious because we just have never had the opportunity to get to them. They have a different type of an orbit than a planet in order to get to them. It's very difficult to consider landing on a comet. That's almost impossible this day and age, to land on a comet. We just don't know what they're made of, how they react to different materials, how hard they are, how soft they are at the core. People might remember some of the movies a few years ago that talked about comets coming towards the Earth. Now, the data that they're getting from this type of mission could give them some clues to how to deal with that potentially in the future. What if one of these is to go towards the Earth at some point? And we should point out, too, that this collision with the comet will not steer it out of its orbit. It's not going to start hurtling towards Earth because of this, simply because the impactor itself is so small and the comet is so large. Even though they had this big explosion, it's not going to change the path of the comet or steer it towards Earth in any way. But they really are very mysterious. The ice and debris and dust that make up a comet are a huge mystery to scientists and could really provide some amazing insight into the history of our solar system.
Daniel Seberg, thank you very much indeed. Daniel Seberg there, CNN technology correspondent, updating us with the very successful, it seems, outcome of the Deep Impact mission, which basically hooked up a small probe weighing about 800 pounds with a comet known as Tempel 1 in order to bring back some material, to analyze, to essentially bash some material out of below the surface of that comet and allow scientists, using things like the Hubble telescope, to work out what exactly is within that comet.
Team, we got a confirmation.
Okay, we got a confirmation. Oh my God, look at that. Oh yeah. Put that up on the screen.
Stephen, there is an incredible image you have to put up on the screen.
Oh, that's got to go up on the screen. Oh, look at it. Oh, yeah!
Impact. I mean, you got to get it up there. It is an amazing image.
Yeah, that's a keeper.
That's...
Impactor flight. This is flyby fall protection. Go ahead.
Oh, yeah! You got to put that image up. Oh, yeah! Look at that! Oh, we hit that record. That's pretty. That's awesome. That's awesome.
That's plenty of confirmation right there.
Yeah, that's plenty of confirmation. That's right. There's no question about it. There it is. There's the impact image confirming impact, but not only that, but it's considerably brighter and considerably more material coming off than I thought. But the predictions on the science team are all over the map. Somebody won a fairly large-sized pool here with a long shot prediction on a rather extraordinary impact. I mean, we've got an object the size of a washing machine that's going in here and creating a crater and ejecta that's just enormous. Or at least that's the way it looks like now. But we'll have to analyze that as the days go on. One of our science team members actually predicted that the impact would release subsurface pressure and we'd have a far bigger explosion than we anticipated. That maybe would happen. I don't know. Yeah, this is the pre-impact ITS image. This is the impactor just before it vaporized itself, along with 600,000 names of folks who wrote in and had their names inscribed on a chip at the front end of this impactor. I'm sorry, folks, those 600,000 folks, their signatures are no longer. Okay, you can see some circular features just as the impactor is getting ready to collide. Now, whether those are impact craters or whether they're simply sinkholes from vaporization is a question that's going to have to be answered by our science team. And it's going to take a few days to do that, perhaps months. But you can see features on the surface here that are down at the few meter resolution. That's several times better than we've done before on comets. This geology, or cometology, if you will, is really quite remarkable. You've got some debris down the southern end there. You've got circular craters. You've got ridges. You've got what looks like I'm sure it's not a pond, but it looks like a smooth area up in the upper right, or upper left rather. You've got everything that a geologist would love here. It's going to take, and one of the ways we can actually analyze the heights of these features is to do stereo pairs, and that'll be coming later. You can actually put the images up next to each other with stereo glasses and see just how steep some of these crater walls are.
Okay. Meantime, here are some images coming into the science team area. Those are pictures taken directly off the screens and being projected on the screen in the science area.
Yeah, these are some pre-impact images that are being taken right off the wall from the science team. You can see what looks like degraded images as the mirror is being sandblasted toward the end. I think that's what's happening. I won't swear to it, but I think that's what's going on. Okay, this is one of the last images sent down by the impactor just before checking out. You can see the bottom terminator, we call it. The sun is coming up from the bottom and right, and it's illuminating some extremely interesting surface features. That's going to keep the scientists going for a long time. But the navigation was perfect and couldn't have been any better. The impact was bigger than I expected and bigger than most of us expected. So this is going to tell us a great deal about how this comet is put together, whether there was an interior pocket of gas that was released. We haven't had any information from the spectrometer, but it's not out of the question that the spectra after the impact will be completely different, or at least a bit different from pre-impact spectra, suggesting that we've released subsurface materials that we hadn't seen before. We'll be looking at that. Certainly the water production rate went up as a function of the impact because we released interior, we excavated interior ices, and those ices were vaporized in the sunlight. So we'll be looking for just how much water production rate increased, how much the carbon dioxide gas production rate increased, how much the carbon monoxide gas rate increased. All of these gases are present in the icy form. It's mostly water ice, mind you, but there are more exotic ices there. Carbon monoxide, carbon dioxide, perhaps cyanogen, we don't know. That'll come out of the IR spectroscopy. My Lord, look at that resolution. It's really quite extraordinary. We're getting down to several meters resolution just prior to the impact itself. I can't imagine how this could go any better.
Now, the team has no idea what kind of surface it will find, if it's ultra hard, if it's soft, and what kind of crater you'll get.
Well, the whole objective of the mission is to analyze the development of that crater we saw and the ejective curtain that we saw coming off, and then and then ask the question, what kind of an interior cometary model would produce that type of an explosive event? And there are several models that could explain almost the entire range of cometary phenomena. So by observing the crater formation process, how fast it develops, how much material is ejected from the crater, we can back down and determine just how this comet is put together. Now this is another image just prior to the impact. I don't know it for sure, but it looks to me like we've got a few meter resolution, perhaps sub-meter resolution, which would be unprecedented. So we got some white features there, we've got some dark features, we've got some what appears to be ridges. Certainly it's rough terrain. It's unlike anything we've seen before, that's for sure. Perhaps those are pockets of ice, I don't know. It's going to take a long, hard look at these images to figure out just what's going on here, but we've got all the data we could possibly ask for, and the science team is ecstatic. Not a one of them can believe they're being paid to have this much fun. All right, down at the bottom you can see the X where the auto nav is sending the spacecraft. We're getting right. You can see some circular features. X marks the spot where we're headed for impact. And the southern end of the comet, the flyby spacecraft will go right underneath. The spacecraft is not going to last much longer, but it's doing pretty well. It's not being buffeted by dust particles. The camera is not being sandblasted by the particles, at least not obviously. Whoops. Maybe I spoke too soon. Look at the circular features. This is the highest resolution we're going to get from the impacting spacecraft. It's getting down to a few tens of meters resolution. We're seeing objects very circular, and the spacecraft's doing remarkably well for something that's about to vaporize.
Flyby contact. Go ahead. We got our expected proper command for the kill sequence. Copy that.
It's getting closer, closer. Oops. We may be getting some serious dust hits, perturbing the telescope, or sandblasting the optics of the telescope. We expect that. Yeah, the image is being degraded. Our brave little spacecraft is in a very hostile environment here. Look on the right, you can see the circular feature. So that we're down to a few meters resolution here. These images will get much, much better as we gussy them up after the fact with computer enhancements. I think we're... Okay, we jump back.
Flyby science is flyby flight.
We jump back in time.
Can you report when you expect to see the first images on the ground of the impact event?
Okay. Yeah, we're going. The impacting images are getting less and less focused. We're expecting to lose the spacecraft any minute here. But it's doing one heck of a job just before checking out.
Go ahead, flight software.
Can't believe they're paying us to have this much fun.
Foxtrot and an associated sequence run error increment of 4 as expected.
Copy, thank you.
These images are coming right from the science room projection, so that they're not nearly as good as they will be. Looks like our intrepid little spacecraft is having some problems with the mirror, probably being sandblasted by the dust particles. It's running in at 6 miles per second. At that rate, you can go from Los Angeles to New York in just over 6 minutes, or around the world in just over an hour. We're going not only faster than a speeding bullet, we're going about 10 times faster than a speeding bullet. And that puts Superman to shame.
Gesehen haben. Und jetzt versuchen wir aus den Bildern, die die hochauflösende Kamera bringt, zu erkennen, wo der Krater ist.
Ja, Sie haben gesagt,
es wird noch ein bisschen dauern.
Okay. Was erwarten Sie sich denn? Was wollen Sie denn herausfinden genau? Wird das, was Sie da heute herausfinden können, unser Wissen über Sonnensysteme, über Planeten völlig auf den Kopf stellen können?
Es wird zunächst mal unser Wissen über die Kometen erweitern. Und wenn man das erstmal weiß, wie der Komet von innen aussieht, dann kommt erst die zweite Geschichte, wie weit uns das Hinweise auf unser Sonnensystem und dessen Entstehung geben kann. Das wird aber sicherlich eher Wochen und Monate dauern, bevor man dazu kommt. Ich hoffe, dass wir bis Mittwoch in etwa mal so eine Grobauswertung der Bilder hat und dessen, was der Krater uns zeigen kann.
Herr Kissel, erklären Sie uns noch ganz kurz, wir sehen hier auf den Bildern, die wir hier nach Deutschland überspielt bekommen, immer wieder so Art blitzende, sieht aus wie so eine kleine Diaschau, dann immer wieder ein Bild mit einem, ja, da sieht man wohl den Kometen, verschiedene Krater. Was ist das genau? Können Sie uns das beschreiben?
Na, ich kann das im Moment auch nicht sehen. Ich sehe nicht, was Sie kriegen. Ah ja, doch, da hinten ist nach der TV. Ja, da sehen Sie die Oberfläche und Krater. Ich sehe die Bilder, die die Kamera aktuell liefert, und da sieht man die Ecke und man sieht oben noch den hellen Auswurf, aber den Krater kann man noch nicht erkennen.
Okay.
Und eben, als die geklatscht haben, ist der Michael Hearn reingekommen, das ist der PI für diese Mission, und von ihm fällt auch einiges an Spannung im Moment ab.
Das ist der PI, was ist das?
Bewegt. Der Michael Hearn, der ist der PI für die ganze Mission,
ja.
Und der ist, von dem fällt die Spannung jetzt natürlich auch ab.
Okay, Herr Kissel, ganz herzlichen Dank. Von Ihnen fällt die Spannung sicherlich noch nicht ab. Wir warten ja noch auf die vielleicht ersten Ergebnisse. Herzlichen Dank für den Moment nach Pasadena. Und wir machen hier weiter in Berlin mit der großen Politik. Was reden die da? Die NASA hat zum ersten Mal überhaupt in der Geschichte einen Kometen bombardiert geradezu, um rauszufinden, was im Inneren dieses Kometen los ist. Das hat die heute früh gemacht. Wir haben es live im ZDF-Morgenmagazin Ihnen zeigen können. Wir werden das gleich auch noch mal ein bisschen auswerten, vielleicht schon erste Ergebnisse sehen.
Und nochmal Bilder, jetzt dann die Bilder tatsächlich von dem Einschlag hoffentlich. Und sind sehr gespannt, was sich da in 133 Millionen Kilometer Entfernung von uns getan hat.
133 Millionen Kilometer. Das ist Fernsehen, oder? Dauert nur 7 Minuten. Ganz locker. Noch schneller geht's, wenn Sie uns anrufen. Egal, wo Sie wohnen, richtig oder falsch. Die Nachrichten.
Guten Morgen, liebe Zuschauer. Vor etwa einer halben Stunde ist ein bisher einzigartiges Experiment der Raumfahrt geglückt. Die US-Raumsonde Deep Impact hat erfolgreich einen Kometen im All beschossen. Großer Jubel bei den Wissenschaftlern im amerikanischen Kontrollzentrum in Pasadena, als erste Fotos vom Einschlag in den Kometen Tempel 1 eintreffen. Das Geschoss traf den Himmelskörper mit etwa 37.000 Kilometern pro Stunde. Beim Aufprall entstand eine riesige Wolke. Die gesammelten Daten werden von der Raumsonde Deep Impact an die Erde gesendet. Von ihnen erhoffen sich die Wissenschaftler, mehr über die Geschichte unseres Sonnensystems zu erfahren.
Um 8:30 Uhr haben wir es jetzt. Dies ist am Morgen bei NTV. Schön, dass Sie dabei sind. Bei mir im Studio ist Bernd Feuerbach vom Deutschen Zentrum für Luft- und Raumfahrt. Wir sprechen gleich über das Thema. Schön, dass Sie da sind, dass Sie da geblieben sind. Herr Feuerbach, es ist unbestritten, meine Damen und Herren, der Crash des Jahrhunderts. Erstmals in der Geschichte der Raumfahrt ist ein Himmelskörper von Menschenhand beschossen worden. Pünktlich zum Unabhängigkeitstag der USA am 4. Juli, Stichwort Independence Day. Sie wissen, was ich meine. Der Film hat die NASA ein kleines himmlisches Feuerwerk gezündet. Ja, das lassen wir einfach mal so. Ein greller Blitz und Begeisterung im Kontrollzentrum in Pasadena in Kalifornien. 7:52 Uhr, kurz vor 8 Uhr mitteleuropäischer Zeit, schlägt das Projektil auf mit 37.000 Stundenkilometern auf Tempel 1. Eisstein, Gestein. Staubfliegen in den Weltraum, angeleuchtet durch die Sonne. Durch den Aufprall des etwa kühlschrankgroßen Geschosses entsteht ein riesiger Krater. Hier nochmal eine Animation vorher. Sie sehen es, 337 72 Kilo ist das kupferne Geschoss schwer. Es war 24 Stunden zuvor abgeschossen worden von der Raumsonde und ist ganz planmäßig auf Kollisionskurs gegangen. Aus sicherer Entfernung 8600 Kilometer, die Bilder, die wir gesehen haben. Ist das wirklich so, um das mal so aufzunehmen, ein kleiner Schritt im Weltraum und ein Riesenschritt für die Menschheit, was da passiert ist? Erfahren wir wirklich heute so viel?
Ja, das kommt noch. Also erstmal Gratulation an meine Kollegen in den USA. Tolle technische Leistung, ja. Fantastisch. Ein tolles Feuerwerk für den Unabhängigkeitstag. Wissenschaftlich ist das sicher ein ganz, ganz wichtiger Schritt. Die eigentliche Wissenschaft fängt aber jetzt erst an. Was man jetzt gemacht hat, man hat eine Wolke von dem Material aus dem Inneren des Kometen herausgebracht. Diese Wolke wird jetzt beobachtet, einmal von der Sonde aus, aber dann von sämtlichen Teleskopen auf der Südhalbkugel der Erde und vom Hubble-Teleskop und von der Rosetta-Sonde. Das ist eine europäische Sonde, die gerade unterwegs ist, um später auf einem Kometen zu landen und ähnliche Untersuchungen wirklich vor Ort zu machen.
Welche Erkenntnisse erhofft man sich genau davon? Man sagt also, da könnte man Schlussfolgerungen doch ziehen, wie das Sonnensystem entstanden ist. Warum eigentlich?
Ja, die Kometen sind gleichzeitig mit der Erde und mit der Sonne und den anderen Himmelskörpern entstanden, werden aber ganz am Rand des Sonnensystems in so einer Art kosmischen Tiefkühltruhe aufbewahrt. Und wenn einer von denen nun mal in die Nähe der Sonne kommt und dann hier eingefangen wird, dann kriegen wir eine Information aus einer Zeit von 4,5 Milliarden Jahren, aus der Entstehungszeit unseres Planetensystems. Und wir kriegen also die Urmaterie, aus der unser Planetensystem entstanden ist.
Ist das erstmalig sowas, dass das erstmals Urmaterie zu uns kommt, oder hatten wir sowas?
Also, dass wir sie sozusagen selbst erzeugen,
ja.
bewusst.
Ja.
Jeder Kometenschweif enthält sowas, aber das ist nicht so frisch. Da hat die Sonne schon einige Zeit dran gearbeitet und deswegen zerfallen dann die Moleküle. Und man möchte ja möglichst die ursprüngliche Materie kriegen und die kriegt man jetzt sehr viel frischer. Das ist das Besondere.
Wir sind gespannt, was dabei rauskommt. Ja. Wo komme ich her, wo gehe ich hin?
Ja, die
große Frage der Menschheit, Herr
wie
Feuerbach.
Das Leben entstanden ist auf der Erde, kann damit auch einen ganzen Schritt weiterkommen.
Schön.
Kannst du dir sowas vorstellen? 133 Millionen Kilometer entfernt?
Nee. Das sind mir zu viele Stellen.
Genau, das ist Wahnsinn, oder? Und dauert nur 7 Minuten, bis wir diese Bilder hier auf die Erde bekommen. Eine andere Frage nochmal, die ich ja immer so ein bisschen mir im Kopf erscheint, wenn ich das sehe. Da wird ein Komet bombardiert. Hast du manchmal ein bisschen Angst, dass da irgendwie was schiefgehen könnte dabei?
Naja, das kennt man so aus Filmen, dass da schon ziemlich viel passieren kann, aber jo, das...
Aber eigentlich kein Problem.
Eigentlich, ja.
Du hast es ja im Kino schon gesehen.
Ja, schon.
Und wie ist es bei dir? Ein bisschen Angst, dass es irgendwas hier auf der Erde passiert, wenn so ein Komet bombardiert wird?
Nee, ich glaube, da hat man sich einfach bisher noch viel zu wenig damit auseinandergesetzt und es ist halt auch schon ordentlich weit weg.
Okay, gut. Wie gut, dass es so weit weg ist. Wir sind gespannt auf die Ergebnisse der Wissenschaftler. Erste Ergebnisse können wir möglicherweise jetzt auch hier schon kriegen mit Patricia.
Horst-Uwe Keller an der Seite vom Max-Planck-Institut, der selbst Instrumente und auch Kameras baut, die Kometen fotografieren. Herr Keller, Sie haben die Bilder aus dem Weltall gesehen, heute früh vom Kometen, von dem Aufschlag. Können Sie noch mal sagen, was für Sie schon ein Erfolg? Steht das für Sie schon fest?
Ja, natürlich. Der Komet ist getroffen worden und wir sehen eine ganz deutliche Reaktion des Kometen. Wir haben gesehen, dass es eine große Staubfontäne gegeben hat und da ist Material, Staub auf der einen Seite und aber auch Gase werden freigesetzt und die können jetzt chemisch analysiert werden und wir werden daraus lernen, wie das Innere des Kometen aussieht.
Wir gucken uns vielleicht mal die aktuellen Bilder an, die Tim Kröger für uns zusammengefasst hat. Wenn wir das schon
genau 7:52 Uhr am amerikanischen Unabhängigkeitstag. Jubel in Pasadena, Florida. Der Deep Impact, der tiefe Einschlag in den Kometentempel 1 ist geglückt. Ein weißer Blitz zeigt es an. Jetzt hoffen die Forscher auf Erkenntnisse über diesen Vagabunden vom Rand des Sonnensystems. Gestern Morgen bereits hatte die Sonde Deep Impact ihr Geschoss abgeworfen, das mit 37.000 Stundenkilometern mitten in den Kometen krachte. Die Forscher erhoffen sich einen schönen tiefen Krater und möglichst viele schöne Bilder vom Innenleben des Kometen. Der Zweck von Deep Impact ist es zu verstehen, ob es Unterschiede gibt zwischen dem, was man von außen sieht, und dem Kern. Sind Kometen nur schmutzige Schneebälle, die sich früher oder später auflösen? Oder steckt unter der Oberfläche etwas noch Unbekanntes, Festeres? Aus sicherer Entfernung beobachtet das Mutterschiff die Kollision und sendet die ganze Zeit über Bilder. Dafür bleibt gerade mal eine knappe Viertelstunde Zeit nach dem Aufschlag. Möglicherweise ist der Komet poröser als gedacht und fällt auseinander. Aber auch das brächte wichtige Erkenntnisse für die Forscher. Minütlich erreichen nun neue Bilder vom Tempel 1 die Erde. Weiterhin viel Arbeit für die Wissenschaftler.
Horst Uwe Keller, wir haben es gerade noch mal gehört, die 15 Minuten nach dem Einschlag sind eigentlich die wichtigsten gewesen zum Sammeln der Informationen. Warum? Was ist da in diesen 15 Minuten?
Sie haben ja gesehen, während des Einschlages hat es eine große Staubwolke gegeben. Und da konnte man eigentlich die Oberfläche selbst gar nicht sehr gut beobachten, sondern da muss man erst mal warten, bis sich der Staub sozusagen gesetzt hat. Und das dauert ein paar Minuten. Und dann kann man sich angucken, welchen Schaden in Anführungsstrichen der Einschlag gemacht hat und kann den analysieren und daraus ganz genau lernen, dann, wie steif und wie fest die Kometenoberfläche ist.
Um 7:52 Uhr war der Einschlag, dann also die entsprechenden 15 Minuten, dann die entsprechenden Minuten, bis das Ganze zur Erde gesendet wird, 7 bis 8 und dann wiederum, bis die Bilder bei uns ankommen. Jetzt sind sie aber da. Wir gucken sie uns mal gemeinsam an. Die ersten Bilder also von nach dem Einschlag. Ich hoffe, wir können sie sehen. Da ist er. Der Komet.
Das ist ein Teil des Kometen, nämlich die sonnenbeschienene Seite des Kometen. Und im Schatten kann man ihn nicht erkennen. Der ist größer, als man ihn hier sieht.
Das ist jetzt im Moment noch der unversehrte
Das ist richtig,
Komet.
ja. Und das sind Teile der Oberfläche vom Kometen. Da sieht man, dass er sehr rau ist, sehr strukturiert ist, übersät ist mit Pockennarben, wenn Sie so wollen. Wie typisch, wie wir das auch bei anderen Kometen gesehen haben.
So, und jetzt hier?
Und das scheint das gesamte Bild des Kometen zu sein, auch von etwas größerer Entfernung.
Aber jetzt mit Einschlag?
Ich kann das nicht erkennen. Der hellste Punkt ist der sonnenbeschienene Punkt und dort ist hat der Einschlag stattgefunden. Ja.
Aha. Okay, also das heißt, aus diesen Bildern wird man jetzt auch erstmal noch nicht schlauer, oder wie?
Na gut, ich meine, da muss man ja sehen, dass man ja nicht ganz genau weiß, wann die gemacht worden sind. Ich glaube, dass die Bilder gezeigt haben, den Kometen von einer größeren Entfernung vor dem Einschlag. Die letzten Bilder.
Wir haben dann gesehen, dass sich die Kollegen in Pasadena wahnsinnig gefreut haben.
Wir haben den Einschlag selber gesehen, wir haben ja die Staubfontäne gesehen.
Richtig.
Und jetzt werden wir noch mehr Bilder sehen, die kommen. Das dauert halt ein bisschen.
Können Sie uns noch mal sagen, was nun das Bahnbrechende ist? Also abgesehen davon, dass es zum ersten Mal war, dass Menschen tatsächlich einen Kometen beschossen haben, bombardiert.
Der entscheidende Punkt ist, dass wir ja schon mehrfach Kometenkerne beobachtet haben, die man sowieso von der Erde aus nicht sehen kann. Da muss man heranfliegen. Und der entscheidende Punkt dieser Mission ist, dass es uns gelungen ist, zum ersten Mal in den Kometenkern hinein einzudringen und von da sozusagen Materie freizusetzen, die rausspritzt. Und diese Materie kann man untersuchen. Man kann also sehen, wie der Komet wirklich aufgebaut ist im Inneren und nicht nur die Oberfläche, die schon ausgedörrt ist von der Sonne, dadurch, dass der Komet ja sehr häufig schon an der Sonne vorbeigeflogen ist und die flüchtigen Stoffe dann immer weniger werden und die ganze Oberfläche ja nicht aktiv ist, sondern nur kleine Teile, vielleicht 10% sind aktiv und produzieren das, was man als Kometenbild sieht, den Staub und das Gas. Und jetzt hat man ein Loch gemacht, das selbst aktiv werden wird, wenn die Sonne drauf scheint. Und aber der entscheidende Punkt, die Sonne ist mehrere Meter oder zig Meter in den Kometenkern hinein eingedrungen und hat von da aus Materie freigesetzt.
Vielen Dank, Horst-Uwe Keller. Die Kameras, die Sie unter anderem bauen, helfen bei solchen Sachen. Sie sagen es, man muss ganz nah ranfliegen oder man muss ganz, ganz starke Teleskope haben, um von der Erde aus was zu sehen. Christian, ich glaube, es gibt da eines, das das kann. Richtig?
Genau, Patricia, wir gucken jetzt mal rüber zu den leistungsstärksten Teleskopen der Erde. Die stehen dort, wo es auch auf der Erde schon wunderschön ist, nämlich in der chilenischen Atacama-Wüste, dort, wo die Luft sehr trocken ist und sehr, sehr klar ist. Und auch diese Teleskope, nehme ich einfach mal an, sind heute Morgen auf einen Punkt gerichtet, 133 Millionen Kilometer über der Erde. Oder, Carsten Thurau, in der Atacama-Wüste?
Ja, die Forscher, die hier am weltgrößten Teleskop in der Atacama-Wüste arbeiten, haben mit sehr, sehr großer Anspannung auf dieses Ereignis gewartet, in 133 Millionen Kilometer Höhe. Es war eine sehr große Anspannung hier zu spüren im Kontrollzentrum der europäischen Südsternwarte. Es sind etwa 15 Wissenschaftler aus den europäischen Ländern, aus Deutschland, Frankreich, Italien, Skandinavien, die mit Deep Impact zu tun haben. Kometenforscher, aber auch Spezialisten für Infrarot- oder Spektralaufnahmen, die sich Monate, zum Teil auch jahrelang auf dieses Ereignis vorbereitet haben. Leider muss man sagen, Christian, dass dieses Ereignis, der Einschlag selbst, von hier aus nicht beobachtet werden konnte, weil durch die eigene Erdbewegung, durch die eigene Erddrehung der Komet Tempel 1 schon vor ein paar Stunden hier vom Blickfeld der Teleskope verschwunden ist. Aber man hat in den letzten Nächten Tempel 1 genau beobachtet, Messungen durchgeführt und wird dies in der kommenden Nacht wieder tun, um diesen Vorher-Nachher-Effekt zu haben, um also zu sehen, welchen Effekt der Impaktor hatte, welche Staub- und Gasmassen dort in die Atmosphäre ausgetreten sind. Das ist genau die Arbeit der Forscher hier in der Atacama-Wüste.
Carsten, erklär doch noch mal bitte ein bisschen, was das Besondere ist an diesen Teleskopen. Warum stehen die ausgerechnet in Chile?
Ja, das Very Large Telescope, so wie es heißt, also das sehr große Teleskop hier in der Atacama-Wüste, ist nicht nur groß, es sind genauer genommen 4 Teleskope, ganz modern, die jeweils in einer riesigen Aluminiumhülle versteckt sind. Teleskope mit einer einzigartigen Lichtsammelfähigkeit. Die Hohlspiegel haben einen Durchmesser von jeweils 8,20 Meter. Diese Aufnahmen haben wir vor ein paar Stunden gemacht. Sie sind in Deutschland angefertigt worden, die Spiegel. Jeder brauchte ein halbes Jahr, das muss man sich mal vorstellen, um nach der Fertigstellung zu erkalten. Und dazu kommen die ganz optimalen Beobachtungsbedingungen hier in der Wüste auf 2600 Meter Höhe. Es ist der trockenste Ort der Welt, Christian. Du hast es vorhin schon erwähnt. 3% Luftfeuchtigkeit im Schnitt. Praktisch keine Lichtverschmutzung, wie die Forscher es nennen. Naja, und Sonne an 350 Tagen im Jahr, damit auch sternenklare Nächte. Optimale Bedingungen also hier zur Beobachtung, auch von Tempel 1 in den kommenden Nächten.
Ganz herzlichen Dank, Carsten Thorau in der chilenischen Atacama-Wüste. Ein traumhafter Ort, auch einfach auf Erden, falls Sie nicht losfliegen wollen, in den Weltraum. Und wir bleiben.
And welcome to NASA's Jet Propulsion Laboratory in Pasadena, California, and happy 4th of July. We're here to share with you the exciting news and the images from our very successful Deep Impact mission to Comet Tempel 1. Joining us tonight this morning, we have Andy Dantzler. He is the director of the Solar System Division at NASA headquarters. Rick Vermeer, the Deep Impact Project Manager from the Jet Propulsion Laboratory. K.R. Patel, the Deep Impact Deputy Project Manager, also from the Jet Propulsion Laboratory. And Dr. Mike Ahern, the Principal Investigator for the mission from the University of Maryland. But before we begin, I'm going to call up the Director of the Jet Propulsion Laboratory, Dr. Charles Alachi, for some introductory comments.
Well, was it awesome? And I was told that we had more hits tonight than the combination of Cassini and MER put together. So that shows you, and it brought the servers down, for a short while. I'm wondering now, there is a comet up in the sky wondering what in the heck hit it. We said this morning that this was going to be, or this is a daring and risky mission. But I can tell you it was. But this dream team from JPL, Ball, University of Maryland, and other universities really made it look easy. And these are the people you see in the white, red, and blue shirts, are sitting in the audience and probably sitting back in the operation room. Now, there is a new trail of exploration for future generations that this team kind of laid out. And what a way to celebrate the 4th of July and the anniversary of our country here. And before I introduce the next speaker, I want to acknowledge 2 very distinguished guests here. We have Congressman John Culberson, who's sitting there, and we have David Southwood from the European Space Agency. And now I introduce the third. And now I introduce the third VIP, who's not a guest, but he's usually here. He's part of JPL and NASA, Al Diaz.
Well, thanks. And let me also say Happy birthday, America. It's great to be here on the West Coast where for the first time in history the fireworks started here. I just wanted to take a second to congratulate the team that made this day possible. It's been a long day, but it's a day that's been the culmination of a long period of effort that a lot of people have made possible. Let me first congratulate the science team led by Mike Ahern for having a great idea, but also having the persistence and patience to make it happen. So congratulations to them. Let me thank and congratulate the NASA centers, not the least of which is JPL for its technological leadership, but also the Kennedy Space Center for its launch, and the other NASA centers for their participation. Let me recognize and congratulate the industry team led by Ball Brothers for the work that they've done producing the hardware that made this day possible, both the spacecraft and the imaging systems. Finally, let me thank all our partners and congratulate them. As has been said before, the science that comes out of this mission will be enabled by an array of dozens of assets that have been pointed at this event, and those assets are controlled by all of our partners, both domestic and international, and it's nice to have David Southwood here from the European Space Agency, who's played such a critical role in making this a success. So congratulations, and thank you all for being here.
All right, we'll start right now with Andy Dancer.
Thanks. Well, what a smashing success, huh? I can use it. Look, I know that most of you want to hear from the engineers and scientists on the panel. I won't prolong this very long day. I do want to point out that this has been, as the two previous speakers said, quite a success, quite a hit for NASA. Quite a success for teamwork in general. The team of university, NASA Center, NASA headquarters, Ball Aerospace, a wonderful collaboration around the world, including the European Space Agency Rosetta spacecraft. And also, it's quite a success, quite a hit for a program, the Discovery program, that knows how to pick the best of the best. Just in case you missed it, we have a picture of the impact. There it is. That is phenomenal. I was trying to think of how to describe this, and I'm just plain speechless. I know Rick is going to go more into just how close this is to how it was modeled, but I have to say, I don't think anyone expected it to go this beautifully well. So on that high note, I'll stop gushing and pass it off to Rick.
Thanks, Andy. Well, I'm more relaxed than I was the last time I was up here, that's for sure. Give you a little status on the mission. Right now we're -1 spacecraft, the impactor. It's been totally vaporized per plan, and we were right on target, as you've heard, and we have a healthy flyby spacecraft, and Kara will talk to that some more. If I could get the first image. This is kind of an interesting compilation, if we can get the roll. Starts out with the animation video. As you can see, we've shown it many times, and you see the impact here. But what's interesting when you look at this is there's the impact that actually occurred. It came together quite well. Just phenomenal. It went very much like clockwork. We didn't exercise a single contingency plan that we had. And we stepped through everything just like it should have been. If I could get the next roll. What you'll see here, of course, is the team reaction when we actually could confirm that we hit.
Team, we got a copy.
This is, I have a fun crew, what can I say? This, you know, to say to the team members out here, just one heck of a job. We couldn't have been here without a lot of teamwork, and my thanks goes out to all the team members who worked very hard, spent a lot of time away from the family, worked a lot of holidays. You guys did a great job, and everybody should applaud you for it. And then, of course, we had to stop celebrating real quick and go back to taking care of the flyby. But what I'd also like to show you next is, if we could get the next row on here, is actually a bird's eye view from the impactor's viewpoint coming in to the comet. This was just phenomenal as we were coming in and doing the trajectory correction maneuvers of it. And you can see it all the way up to the end. We actually, I seem to remember a previous news conference, we were telling you that we had a requirement to get a picture about 30 seconds out from impact. And what you saw here, we got the last picture was 3 seconds before impact. Just phenomenal. So it was great. I think we've provided the science that Dr. Hearn and his team can chew on for quite a while. And with that, I'll turn it over to Kayer, the deputy manager, who will talk on the flyby.
Wow. First of all, I want to congratulate and thank the team for an outstanding job for making this happen. We couldn't have done it without them. Flyby is performing amicably. After the separation event, it headed towards the spot where it needed to be to photograph the impact. And once it did so, it went into shield mode for closest approach, and it came out the other side with not a single system damaged. So the flyby is doing great. The first picture that you will see here is a picture from the impactor as it's going in, and taken from the ITS camera. And as you saw in the prior video, the impactor went and hit the comet in a specific spot. The flyby's job was to image that spot, and between the two of them, the coordination, we had the spot nailed to less than 50 meters off. So the flyby imaged the spot within 50 meters of where the impactor hit. So that's just amazing. Can I have the second one, please? This is from the flyby perspective as it's looking and imaging the impactor going in and hitting the comet. So this is just incredible. So with that, Mike, it's all yours.
Thanks. Most of the rest of the team got thanked, but I want to thank Kayer and Rick particularly for bringing this across. And we pulled out, I just have a few still images to show you, but I need to tell you that as we were sending the images off to be prepared for this press briefing, we were of course still watching the images that were coming down, and there are many more spectacular images yet to be revealed. First, I'll just show you two impactor images, picture of the whole thing. These are in the clip that Rick showed. So there's the whole comet. It's about 5 kilometers across, sort of 7 or 8 kilometers long in this projection. But it rotates around this way, so we're not seeing the full long dimension of it in this picture. The next is one of the close-up images. That picture has a scale of about 7 meters per pixel. The big crater has a diameter of about 1.5 kilometers, something like that. So we've got by far the highest resolution images of cometary nucleus ever from the impactor, and we haven't, not even counting what we'll get from the flyby. So the impactor was perfect. The flyby instruments also work beautifully. We got tremendous spectra, new spectral features, really strong spectral features, great thermal spectra. I'm not going to show you any of those. They just take too much interpretation. So I'll show you an MRI image of the impact, which is the next still. And the next image shows you what you can do when you start working with the HRI, and you all know the HRI is a little bit out of focus, but you put some deconvolution on it, and you can recover a fair bit of resolution. So we haven't worked out what the resolution is. We finished doing the deconvolution with 1 minute to spare to get the image over here for processing. So the flight team has completed most of its work. We're just basically starting our work now, trying to make sense of what we've learned. Obviously, it was a very big impact. Presumably, we have a large crater in some one of those images that hasn't played back yet. The interpreting the ejectocone, we obviously have lots of images of the ejectocone. Interpreting that's going to take a little bit of time. There are lots of structure in it that's of interest to understanding the nature of the comet. We'll be working that out over the next half day and weeks and months and years. And I just look forward to a wealth of data that will take me to retirement.
All right, we're going to go ahead and start taking questions here. When you raise your hand, would you please wait for me to call on you and get a microphone to you so we can hear your question, and then please state your name and your news organization. Where should we begin?
Brian Cox, BBC. Are you confident you're going to get some good images of the crater? I mean, is that big bright flash going to die down, in your opinion?
Well, no, we'll have to wait and see. We only have 10% of the data now.
Yeah.
The rest comes down over the next day.
Okay. Bill Harwood, over here.
Bill Harwood, CBS. So you said, Dr. Hearn, you were still seeing stuff coming in as you walked over here. Is the evolution of the ejectocone proceeding? Is it dying down? Do you see any trends you can tell us about over, I guess, that 45-minute time scale?
It was still a very good, bright ejectocone, much larger than the cometary nucleus in the first look-back imaging, which is 45 minutes later. That much I can tell you. That was the image that came down 5 minutes before we left to come over here.
Gary Robbins.
Gary Robbins at the Orange County Register. From the size of the flash, can you tell anything about the amount of material that was ejected, and is it too early to tell anything about the chemical composition of it?
We've made some crude estimates of the amount of material from the brightness of the flash, but I think we're going to hold them till we think about them a little bit, and we may or may not discuss those at the briefing at 11 o'clock this morning. And the composition, there are unidentified spectral features. Obviously, we can't tell you what they are. Not yet.
Hi. Anthony Cabrera with Space.com and Space News. Has any information started coming in yet from Hubble and Spitzer and some of the ground-based telescopes that we're monitoring?
Yeah, they observed a brightness increase of about 2 magnitudes, which corresponds to a factor of 6. Both ground-based and Hubble observed that kind of brightening. A few telescopes reported big increases in the emission lines in the spectrum. So they're getting lots of results also.
Okay, in the back.
Mark Horseman, ABC Television in Australia, and looks like honorary member of the Impactor team. Can you tell me, could you have pulled this off without the radio telescopes in Australia?
No, obviously not. We needed the communications, and we've been using those assets all along for quite a while, and in fact almost constantly over the last two or 3 weeks. In addition to that, since this is one of those one-time shots, we wanted to make sure that we had overlapping coverage and made sure that if we had one station, say Madrid or Canberra, that we had them overlap so that we had time for the handoff and not to lose data. So it was very essential that we had this in order to perform the mission and get the data back. And we're still going to be using them to get the data back.
Aside for a moment, please, gentlemen. What message are you sending to the world by shooting a comet on the 4th of July?
I'll think about that. I don't think we started out to send any message at all. Actually, we're actually performing a science mission, and as you can see, and from listening to Dr. Ahern, we have a lot of science to be had here. That being said, I obviously hope that it's made America proud to see that we overcame a lot of challenges. A lot of people said we couldn't do this or wouldn't be able to pull it off, and the team stuck together through a lot of adversity and problems to work out and made it happen, and it happened like clockwork, and I think that's something to be proud of on America's birthday.
Begley out of the Washington Post. For Rick, could you describe what happened during the 3 course corrections that the impactor made? As it made its last approach? How long were they? Did the impactor really need to bother? I mean, were you that much on target? And just how did that go?
Sure. And I'll probably ask Kerr for some help if he remembers all the numbers. But basically, yes, in answer to one of your questions, yes, we did have to bother with it because obviously as we're closing in, the comet's moving too, and as we had briefed before, we didn't know the exact size and shape of this comet and had to do some final adjustments as we were coming in. So the first ITM at 90 minutes out, I believe, was 2-point-something meters per second?
1.26.
Okay, 1.26 meters per second. The next one was, oh, you got it all written down. You're doing good here. 2.2 meters per second. And then the third one, 2.3. I can't read your writing. 2.3. Okay, it was 2.3. And that also, from those, after each one was done, then the next cycle would pick up to do the next auto navigation solution, and the result of that would tell us how the first one did, so it then would go and target for the second one. So each time it did one, we got back with the next solution, where it was and how it was getting there. And so obviously our confidence just started increasing, not only as we saw the images getting larger and being pretty much dead on, but we knew that it was making minor adjustments. And we felt pretty good going in those last 30 minutes or so that we were going to have a good day.
David Chandler from New Scientist. For Mike Ahern, I know this is very early, but during the commentary, during the encounter that we heard, Don Yeomans was saying that the size of that plume was very much at the high end of the range of predictions that have been made. Is there anything that you can conclude already from just the sheer size of that plume that was produced? Does that rule out any models or make anything less likely than it was this morning in terms of the structure of the nucleus, its porosity, its density, anything at all?
I haven't even had time to sit down with my cratering experts on the team. So I would be hesitant to speculate, but clearly it rules out really porous structures where you tunnel very deeply, and the impactor just sort of slows down gently, what I refer to as the aerogel capture scenario. So it rules out those kinds of structures without a doubt. I think it probably rules out a strength-dominated cratering, but I need to, before I say any more than that, I'll consult with the cratering experts on the team.
Katie Human from the Denver Post. Were you guys surprised at the spot the impactor picked? And can you tell us briefly why you think it did choose that spot?
Yeah, it chose the brightest spot on the comet, and it performed the first two ITMs, and the last one it did the offset to center to pick that particular spot. The algorithms running on both the spacecraft, the flyby and the impactor, were both aiming at that specific spot, and that's where the earlier statement that the flyby captured this thing within 50 meters of the impact site.
Did you guys find that surprising?
We didn't know what to expect, because as we were going in, we were asking our optical navigation engineers, where's this thing going to go? And based on as they were observing in real time the images, they were kind of saying, I think we're going down here, and that's where we ended up at.
Hi, Larry Evans with Mach 25 Media. I'm curious if you have any idea, recently as you were making the approach, there were a couple of pretty good-sized outbursts on the comet. Can you characterize the outburst that was caused by the impactor in relation to the outburst that we saw naturally?
It was obviously a lot bigger, without a doubt. Beyond that, I can't say much. We haven't had enough time to look at the spectra or look at the shape of the variation of the brightness with time, and that there just requires a little bit more analysis.
Nicola Groom with Reuters. Was the size or shape of the comet dramatically different in any way from what you had been expecting?
Since we didn't know what to expect, it wasn't surprising. We knew from the shape of the light curve that there had to be something that cast big shadows, or we were pretty confident of that going in. And you actually saw that if you were looking at the images 6 hours before impact as we went in. I presume most of the press wasn't waiting with us for all 6 hours. You could actually see a very dark shadowed area come into sunlight very slowly and gradually brighten. So that was the kind of thing we expected. We expected it to be elongated, and we're going to have to go back and work on the stereoscopic combination of images to try to get the three-dimensional shape to find out if it's as elongated as we expected. Haven't had time yet to look at the topography to see if it's anything like either Comet Wilt 2 or Comet Borrelli.
Any more questions here? Yes, David, in the back.
One of the big unknowns going into this was what the fate of the flyby craft would be. Do you have any indications at this time? Do you know whether it survived completely intact, or when will you know?
It survived completely intact. After it went through its shield mode and came out the other side, we did a full health and status safety call on it, and every subsystem was operating nominally.
And given the quality of the image, if you look back images, the optics survived beautifully also.
Any more questions here? Okay. Do we have any calls? Okay. Okay, I think we're going to call it a wrap then for tonight. You're all invited to come back later today for an update briefing that will be at 2 p.m. Eastern Time, 11 a.m. Pacific Time.
Etwa 5 Milliarden Jahre alt, ein Materiebrocken aus Staub, Steinen und gefrorenen Gasen und weit, weit weg. Komet Tempel 1. Der wurde von uns, genauer gesagt von einem kühlschrankgroßen Geschoss namens Impactor, heute Morgen beschossen und getroffen, und die gesamte Wissenschaftswelt jubelt über diese bislang einzigartige Mission, die Aufschluss geben soll über das unbekannte Innenleben von Kometen.
Das sind die letzten Bilder, die das Geschoss vor der Explosion liefern konnte. Tempel 1, der Komet, aus 80 Kilometer Entfernung gefilmt und 130 Millionen Kilometer von der Erde entfernt. Und dann ein perfekter Aufschlag auf der Kometenoberfläche, Jubel im NASA-Kontrollzentrum und Bewunderung bei der ESO in Garching, der Europäischen Raumbeobachtungsstation. Ein spektakulärer Moment in der Geschichte der Raumforschung.
Es war auf jeden Fall ein großer Moment für die Wissenschaft, denn die Mission war ein voller Erfolg. Wie wir ja gesehen haben, ist das Einschlagsprojektil wie vorgesehen auf dem Kometen Tempel 1 eingeschlagen. Wie wir dann auch noch sehen konnten anhand der Aufnahmen, die von der Raumsonde gemacht wurden, die das Einschlagsprojektil die ganze Zeit begleitet hat, dass es eine ziemlich große Aufhellung gab, das heißt also sehr viel Energie wurde freigesetzt.
Im Januar war die Raumsonde Deep Impact ins All geschickt worden. Hier der Ablauf der entscheidenden Situation in der Computersimulation. Der Sprengkörper hatte sich am Samstag von der Raumsonde getrennt und hat dann heute Morgen planmäßig einen riesigen Krater in den Planeten gesprengt. Nun will man mit dem Datenmaterial Aufschlüsse über die Zusammensetzung des Kometen bekommen. Wasser, Staub und Felsbrocken, so glaubt man bisher, aber vielleicht gibt es auch Überraschungen im Herz des Kometen. Wissenschaftliche Teleskope auf der ganzen Welt verfolgen bei besten Sichtverhältnissen den weiteren Verlauf der Mission. Der Start war perfekt, jubelte man in Florida, but the story is starting now. Die Geschichte fängt jetzt erst an.
Was Hollywood auf der Leinwand längst vorgemacht hat, wurde von der NASA jetzt in die Realität umgesetzt. Die US-Weltraumbehörde hat erfolgreich einen Kometen beschossen. Und das auch noch pünktlich zum 4. Juli, dem amerikanischen Unabhängigkeitstag. Auf dem Kometen hat das NASA-Geschoss einen großen Krater und weltweit tiefen Eindruck hinterlassen. Passenderweise hieß die Mission auch Deep Impact. Genau wie der Hollywood-Film, und das ist auch kein Zufall. Hinter der Mission steht die Angst, dass die Erde eines Tages von herabstürzenden Kometen bedroht sein könnte. Da will man vorbereitet sein. 133 Millionen Kilometer über unseren Köpfen hat sich das Bombardement heute früh abgespielt. Bilder und Informationen von Hildegard Wert.
Es war eine Aktion in schönster Wildwest-Manier. Volltreffer über Millionen Kilometer Distanz. Jubel bei den Cowboys von der NASA. Da oben fliegt jetzt ein Komet herum, der sich fragt, was zum Teufel hat mich da getroffen. Es war eine wagemutige und gefährliche Mission. Streng genommen war es allerdings gar kein Beschuss. Die Raumsonde hat einfach ein Hindernis fallen lassen, sodass es die Bahn des Kometen kreuzt. Und weil der nicht bremsen kann, sind die beiden mit Karacho ineinander gekracht. Im Anflug hat der Impactor Fotos geschossen, bis 3 Sekunden vor dem Aufprall. Aus sicherer Entfernung verfolgt das Mutterschiff die Kollision. Tempel 1 wird in die Geschichte eingehen, als der erste Komet, der von Menschenhand verändert wurde. Er ist der Held des Tages, Michael Hearn von der Universität Maryland. Er hat jahrelang immer neue Vorschläge eingereicht, bis die NASA das Projekt endlich genehmigte. Der Hollywood-Film Deep Impact hat dabei Pate gestanden. Da trifft ein Komet die Erde mit verheerenden Folgen. Jetzt hat die NASA den Gegenschlag geübt. Offensichtlich hatten wir einen sehr kräftigen Einschlag und vermutlich finden wir einen riesigen Krater auf den Bildern, die noch nicht überspielt sind. Ich freue mich auf eine Unmenge von Daten. Da habe ich bis zum Ruhestand genug zu tun. Tempel 1 fliegt nach der Kollision scheinbar unbeirrt weiter. Ob er aus der Bahn gelenkt ist, wird sich zeigen, wenn die Astronomen ihn neu vermessen haben. Die NASA hat es so eingerichtet, dass an ihrem Nationalfeiertag nur ein amerikanisches Teleskop den Einschlag direkt sehen konnte. Erst dann kommen die anderen dran. Auch die haben ihre Späher. Das Hubble-Teleskop wird von den Europäern mitbenutzt. Es hat den Kometen heute Morgen hell aufleuchten sehen. Wo es Nacht wird auf der Erde, richten die Astronomen ihre Instrumente auf den verwundeten Kometen. Für die Europäer ist Deep Impact besonders interessant. Denn sie sind die Nächsten, die einen Kometen heimsuchen wollen. Dann aber nicht, um ihn zu beschießen, sondern um weich zu landen im Jahr 2014. Tempel 1, so viel ist sicher, hat den Schlag überstanden und wird wiederkommen. Ganz so leicht ist es offenbar nicht, einen Kometen aus der Bahn zu werfen.
Übrigens nicht nur Wissenschaftler, auch Hobbyastronomen haben ihre Teleskope auf den Tempelkometen gerichtet. Auch von Deutschland aus ist er zu sehen, eventuell sogar mit bloßem Auge. Mehr Informationen dazu finden Sie in unserem Online-Angebot auf www.heute.de.
Good afternoon, and thank you for joining us here at NASA's Jet Propulsion Laboratory for an update on the Deep Impact mission. About 12 hours ago, we made history, and now the science books will have to be rewritten. What we've learned from this impact is beginning to unfold right now at this news conference. Joining us today, we have Andrew Dantzler. Okay, hold on, we are having a problem. We have Andrew Dantzler. He is the Solar System Division Director at NASA headquarters. Rick Gramier. He is the Deep Impact Project Manager at JPL. Sham Bhaskaran. He is the Deep Impact Navigator here at JPL. Mike Ahern. He is the Principal Investigator at the University of Maryland. And Pete Schultz. He is the co-investigator of the Deep Impact mission from Brown University. And we'll start with Andrew Dantzler.
Thanks. So do I have a cool job or what? For the past 6 months or so, what I've done is lead off these panel discussions with one or two liner about the Discovery program and what it's about, how it fits into solar system exploration, NASA goals, etc. But I'm always asked, what exactly is a Discovery program about? What is the ultimate goal? And the Discovery program's goals are the same as solar system explorations and NASA's in general, which really are to enable groundbreaking science, which allows us all to learn more about the world in which we live, the universe in which we live. And in doing that, really push back the envelope of what is generally thought to be possible. And in doing that, inspire or capture the imagination of the general public and hopefully inspire new generations of engineers and scientists to go on and do even bigger and better things. If you need a good example of that, you look at the Deep Impact mission and the events of the past 12 or so hours. Deep Impact is certainly meeting all those goals in spades. I'm very proud to be part of this project, this mission, solar system exploration. It's been a good day for us all, and I'll pass it on to Project Manager Rick Gramier, who will tell us more about the events of the past 12 hours. Thank you.
Thanks, Andy. Good morning, everybody. Let's see, on a personal note, I'd like to report that the team is very tired. However, they're very excited and feeling very proud at this moment, as they well should be. This was the culmination of a lot of hard work on their part, and they deserve to sit back and be able to enjoy the science that we've provided to Dr. Ahern and the science team, and we hope we keep them busy for many years, and we won't apologize for that part. Also, as a note, we have the excitement of this. We're looking at the web hits that have occurred on the website in the last 24 hours, and that's basically about 1 billion hits, which is 2.5 times more than the busiest day that was on for Mars rover. So congratulations, team, and we're glad to hear that everybody around the world is so excited about this. As far as some brief status, I'll give you some brief mission status right now and then turn it over to Sham, who will talk more about the final few hours and minutes of our now departed impactor spacecraft. And I'm happy to report to you that as of this morning, we still don't have an impactor spacecraft, so we're still sure that we hit. And but seriously, on the other side, the flyby spacecraft is in great shape. If I could have the next picture, please. This is a picture that the flyby spacecraft took after it had flown beneath the comet nucleus and it exited shield mode and turned back to take a picture of the receding nucleus. It's absolutely awesome, and you can see the plume and debris from the crater formation being lit by the sun, which is exactly what we wanted to accomplish. And this just speaks 1,000 words. It's an absolutely incredible picture. The flyby itself, excuse me, flyby itself is in good shape. All subsystems are green. We do report that we have just about every single iota of memory storage totally filled right now, and we're going as fast as we can to try and get the data downlinked to the ground stations and get it over to the science team. But all in all, it's still performing like a champ, and it did its mission, and we're happy that it's in that good a shape, and we can get all the data down for our science friends to look at. With that, I'll turn it over to Shan. We'll talk to you about the impactor. Shan?
Thank you. I'm going to give you an overview of what happened with the impactor in the final hours prior to impact. If I could bring up the still image. To do that, I'm going to show you a picture of the impactor taken about 30 minutes prior to impact. At this time, the impactor was about 18,000 kilometers, or about 11,000 miles away. And taking back about 30 hours prior to impact, we did a final targeting maneuver on the impactor from the ground. The goal was to get as close as possible to an impact trajectory, but we had no expectation that it would be on an impact trajectory, but we were hoping to get very, very close to it. The upper left there, it says the pre-release, a little dot with the pre-release. Reconstruction shows that that's where we went, that's where we were going after that TCM, which took us a little off the top corner of the impactor. We're actually very close to being an impact trajectory at that point. Now here's how to make navigators nervous. The first ITM occurred at about 90 minutes out. You can see there on the bottom there, the post-ITM1, the impactor targeting maneuver 1, was actually further away than where we had released it. This wasn't entirely unexpected. We do thousands of simulations prior, in the months leading to the impact, and in a lot of the simulations we had noticed that this phenomenon occurred. So it wasn't unexpected, yet it does make us nervous because we don't like to see things like this, but we were watching very closely. By the time we got to ITM2, just about 35 minutes out, we were actually now, the AutoNav on board had been working and had converged on a solution, and it had gone to pretty much the right place, right about the center of brightness of this nucleus. The third ITM, ITM3, which occurred about 12.5 minutes out, was actually we start from the center of brightness, but then we want to bias the location of the impact to where the flyby spacecraft flies by. And the flyby spacecraft flies by at about a 45-degree angle at the bottom of that image. So the ITM3 took it from the center of brightness to a location towards that where the flyby spacecraft flew. And it all performed very successfully, and this looked a lot like one of our simulation runs, so it was in the end, it turned out very good. And I think the next thing is the movie that shows at a very high speed what the impactor saw at a very compressed time frame. You can see there. There it is, going right to the impact point. And with that, that sort of gives an overview of the navigation for the impactor. I'll turn it over to Dr. Mike Ahern to talk about the science. Impactor targeting maneuver.
Okay, thanks, Shan. Thanks, Natalie. I'm going to show you first a new result that we got last night. Actually, Jessica Sunshine pulled this one together. We now have a map of the temperature all over the nucleus before the impact. We have used the IR spectrometer and combined a lot of spectra to make this image, and the first still shows the visible image on the left, where you're seeing reflected light, and a temperature map. We don't have the absolute calibration on the temperature yet. That'll take another week or two. But that is a direct measurement of the temperature, and you can see the subsolar point is the hottest part, and it's cooler around the parts of the nucleus that have the sun at very low elevation. This will be important to try to understand how rapidly the nucleus responds to changes in sunlight, and that tells us about the structure. More importantly, we now need to go back and do the same thing after the impact and find the cold spot where the crater is, but that's going to be a lot more work. So that's one result we have. I also want to bring up a still image that is the same one that Rick showed, the look-back image, because I want to tell you what this means for the science. We're still doing look-back imaging, doing it periodically, trying to see how long it takes before the special outgassing of the impact event stops. And it's clear that the ejecta were still coming out for at least several hours after the impact event. And this will be important for understanding the nature of the material at the bottom of the crater. If there's a lot of volatiles there, the outgassing will continue to go on for a long time. Yeah, I mean, it could go on for weeks. So that spectacular image is really important for the science. Okay, finally, I'm going to walk you through a couple of the still images from the impactor targeting sensor. They're images that basically are out of the movie that Sham showed you. And they show different aspects of the nucleus that are important to understanding what's going on. First one, the nucleus is completely overexposed. Actually, it wasn't overexposed in the image. We stretched it. We've done a little playing with the image to show the jets of dust, presumably driven off by gas, that are around the nucleus. And this is very reminiscent of what the Stardust mission saw when it approached Comet Wilt 2. Surprising number of jets. Fortunately, they're all relatively faint, which means that it's not too much of a problem for Sham. That was a worry early on with whether those jets would be a problem. Okay, so the next image now actually shows the nucleus itself. We need to trace back all those jets to where they come from on the nucleus. That's the next step. That's a bit challenging. Now, you look at that nucleus, and it obviously does not look like a pickle or a cucumber or the various things we've talked about before. It looks closer to a loaf of bread or a muffin or something like that. You notice a couple of things about it. There is a lot of topographic relief. There are things on this nucleus that really do look like impact craters to many of us. It looks very different from either Comet Wilt 2 or Comet Borrelly, the two comets that we've had close-up imaging of in recent years. We don't understand what this means yet. When Wilt 2 looked different from Comet Borrelly, we thought it might be due to the different orbital histories of the two comets. But this comet's had an orbital history that we think is pretty much similar to Comet Borrelly, and yet it looks totally different. So there's something more going on here that we haven't understood yet. There are lots of bright spots on that image. Most of them are just steep slopes facing the sun, so they get a lot of solar illumination. A couple of them don't seem to be that, and we don't understand them. There are some really smooth areas there, which we also don't understand. And as Gentry Lee is pointing out, it's not even a flat, smooth area like there was on Borrelly. It clearly curves around the side into darkness. We've got to understand what that is. Almost certainly, there is layering. And that's got to be part of what is causing the difference in the nature of topography at different elevations. So there are craters. There's differences in topography due to layering of the surface materials. And there are jets coming from somewhere which we hope to trace out. Now, where the impactor went was towards the bottom of that image, and the next still image is more of a close-up. Again, you see lots of little bright areas. Nearly all of them are simply slopes that are facing the sun. You see the big smooth area in the upper left. Where the impactor went in was just above the lower of the two large craters that are on there. For reference, by the way, if you think back to the previous image, as you see it, the orientation of the comet is really like this. The long dimension is going sort of into the plane of the sky, and it's rotating this way towards you. That top end is coming towards you with the 41 or 42-hour rotation period. We know that from looking at the images from 6 hours earlier. The final image shows a little bit of detail. This is down at 4 meters per pixel, and this is sort of the last image on which you can identify features that were in the previous image and tell us we were just above the crater. So we've learned a lot from these images, but we've learned even more from the cratering event itself, and that's what Pete Schultz will talk to you about.
Thanks, Mike. Our experiment went very, very well. We touched the comet, and we touched it hard. And what I want to show you tonight is, or this morning, it feels like last night, a series of videos, of sequences going through the crater, and I think you'll see some things that look familiar and things that are quite different. And this is just an amazing place to go for the next several months at least. If we could have that first frame grab. This is really a key image because it shows several really important things. First, it shows that extremely bright incandescent ball. Now, some of this is dust being reflected from the sun. A lot of it is actually the incandescent material, that is the self-luminous. If we didn't even have any light shining, we would have taken our own flash picture for ourselves. You also see there's a long, what appears to be gash that's going up. That's not a gash, that's a shadow. That's a shadow of the plume extending across the surface. And I want to give you this one as just sort of a way to get a hint of what we'll see in the next movie sequence, if we can roll that. What you'll see is something really surprising. You'll first see a small flash, and then there's a delay, and then there's a big flash, and then the whole thing breaks loose. This is from the MRI. It's somewhat degraded just because of conversions issues we went through. But what you can see is that this was apparently we may have been able to detect some structuring or perhaps some responses to the impact. Now, this is all preliminary. Our science team has only had a couple of waking hours. I mean, we were up, but I'm not sure if we were awake, living on adrenaline, trying to interpret this. If we go to the next sequence, you can see the HRI that has been processed, and I hope to show you several things in that next sequence if you can. You just got to soak this up. You see the flash, and you notice something in the shadow. We see the shadow evolve, and it looks very similar to some of the simulations that Jim Richardson and Jay Meloss have done based on experiments, where you can follow the ejecta cone out as it advances, and we can see that in the shadow. So this already has an enormous wealth of data. Even though we can't see the actual impact point behind that flash, we can see its shadow, and there's always a lot in a shadow. And what I'd like to show next then is a sequence from experiments, because this looked very familiar. One of the things we were trying to do was to simulate beforehand what we might expect to see with a variety of different models. None of them could have been right. Some of them may have been correct. This was one of the guesses, and what you'll see is the target, and you see the small flash. And now watch this plume come right out of the surface, straight up. And I think this is the shadow that we're seeing, but then you'll begin to see that there's another ring of ejecta in a cone that's coming out, and that casts that other shadow. Now, all this is preliminary, I have to emphasize. And the other thing you'll notice is that The flash wasn't as bright. Well, it turns out you need to add other things, for example, things that will vaporize, and maybe other processes. And that's one of the reasons why we also do computations to balance out what we do in terms of experiments. And so I think we have a lot more to do. I think what we can say, just preliminarily, we can probably say that there was soft layering on top. That's my guess. Soft layering on top, went down, finally got in contact with the ISIS. This was a deep impact, and it got down there. And I think I just have to close with a little comment, is that, you know, I've made a living playing in a sandbox, and now I can say I play on a comet.
And we are going to start here at JPL. Okay, if we can get a microphone here to New Scientist. We'll start here.
David Chandler from New Scientist. Have you seen any signs yet of the crater itself? And do you know yet, if not, do you know what the prospects are for being able to make it out, given that you had such a huge, bright, and fairly opaque plume obscuring it?
We've certainly seen a feature where the crater would be. It's a dark feature. It's unclear whether it is, we just haven't done enough image processing yet to know whether it is the crater itself or a shadow that's laid on top of the crater. That's going to take a little more image processing. We think we'll find the crater.
Okay. We have another question here.
Todd Neff from the Daily Camera in Boulder. How different is the comet's inside, be it ISIS or whatever, than the shell? And have you any notion of that? I know that's one of the key mission goals.
We certainly see big changes in the spectrum as the ejecta evolve through the initial stages. We don't have any numbers on that yet, but there are clearly big changes, so there are big differences in the composition.
Yeah, okay. Right here.
Pete Demetrio, KFWB Radio in Los Angeles. Question, from the preliminary data, do we know exactly how much of the surface and the subsurface layers were ice versus other, components, hard rock, minerals, things along those lines? How soon might you be able to determine that through spectrography or anything else?
I'm not sure if we can really answer that yet. It'll take us some time. We see some changes, which is really great because it says that we might be able to resolve these differences. But it's going to take some real time, some debate among the science team members. My guess, first guess, is that it's down there, it's deep, but how deep, I can't tell you yet.
If you would quickly, given what you've seen of the plume, does it approximate or compare in any way, shape, or form with what you've done in theoreticals in the laboratory of ice versus solid material?
There was a lot of dust that came out, and we assumed that that's the dust. So, which is kind of expectation, what you might expect for something that is a middle-aged comet. But that ratio, we need to do more analysis, both with spectroscopy as well as with the imaging, and from the observatories. This is going to take a long time to integrate everything, and this wasn't just a simple experiment. We had a lot of eyes watching.
San Diego.
Hi, Bruce Lieberman, San Diego Union Tribune. Can you tell us how far away the flyby spacecraft was from the comet on that first image you showed? And then, secondly, you had mentioned that the ejecta will be, the ejecta plume will be present for a long time. Can you tell me what that shows about the comet?
I'll give you the distance. First image would have been somewhere around 8,500. Just before the impact would have been somewhere between 8,500 and 10,000 kilometers. You think of the first image that Pete showed?
The look-back image with the
the look-back imaging.
Bright plume, yeah.
Oh, the look-back imaging. I'd have to calculate it. Come back to me in 2 minutes.
In those 2 minutes, we're going to take a call from CNN. Brian Todd, are you there?
Yes, can you hear me okay?
Yes, we can.
Just curious, could what we learned from this mission and what you've seen so far today help us on Earth sometime in the future, possibly deflect a comet or an asteroid if one came near Earth or within threatening distance of Earth?
The knowledge that comes out of this after we finish analyzing the data is important to understanding how to deflect a comet. Any serious attempt to deflect a comet with an impact, however, requires a much, much larger impact than we delivered. The orbital change from our impact is predicted to be so small that it is unmeasurable. But we can measure things like the amount of material that comes out compared to the amount of material that we put in, and that gives us some idea of the efficiency of changing the momentum of the comet.
Okay. We are going to come back here to JPL. We have one right up here in the front. Jim Erickson.
Jim Erickson from the Rocky Mountain News. In that look-back image, do you have a ballpark number on how far out that cloud of ejecta is in kilometers? What's the distance that stuff is extending from the surface, roughly? And is the correct word, would it be mostly dust, or what is the correct word to use on what that stuff is made of? Dust and ice?
Okay. Since you brought the subject up, let me first answer his question. The distance of the spacecraft was about 27,000 kilometers when that image was taken. Those ejecta go out thousands of kilometers at least. Whether they go further requires more image processing to know. It is certainly largely dust. We see mostly dust in those images because that's what's reflecting the sunlight. And by then, that early flash that Pete talked about has cooled off. On the other hand, there's probably water vaporizing from ice that is driving some of that. So there is gas with it, but that's not what you actually see in the image.
We have another call. Science News. Ron Callan.
Yeah, two questions. First, is there a minimum temperature that you know this ejected dust has to be? Because, Mike, you said that it was, I guess, warm enough or hot enough that even if the sun wasn't there, you would still see it. Does that suggest a minimum temperature?
Yeah, I'm sure it's going to be thousands of degrees Kelvin, but that doesn't still answer your question. I think rather than talking about minimum, I think we have a whole host of instruments on board, and I think we can actually answer your question much more clearly with real answers rather than simply speculating here. But it was very hot. You get that when you're slamming in at 6 miles per second. Can't help it.
The other question is, people sort of asked this before, but is there a statement you can make that this comet is less souffle-like and more solid just from the energy and brightness of the outburst? Is there some statement you can make, preliminary one, about the structure of this comet?
Yeah, I think preliminary, it indicates, to me at least, that this was probably a soft surface, a dusty soft surface on the very top, and then the stuff below. And I don't think that the model of having, at least for what we can see, is a very thick, hard crust. Now, that doesn't mean that doesn't exist. We are looking from a distance, and there's a lot of material that is being obscured by the material coming out of the event itself. So there still may be things in there that tell us much more yet. It just is really going to require some detailed image processing.
Okay. Thank you. We have a call. I'm sorry. We have a reporter here.
Yeah. Good morning, Elizabeth Espinosa with Fox 11 News Channel Los Angeles. Good morning or good evening, whatever you're feeling at this point. You showed us an image a little bit ago of, it looked like a tunnel. Is there any way you can put it back up there and kind of walk us through what we're looking at in terms of the angle? There was a light that came through. If you could really explain where, how the angle and what we're looking at there, so we can explain it to our viewers who aren't as scientific as yourselves.
I'm not sure which image you mean. Which one of us used it?
That I don't remember, but I believe it was the one with, it looked like a tunnel. There was a light coming through. Yeah, I
But
want
the
to
look
look
back
back.
image,
Yeah.
so the one that we used twice, Rick and I both used it.
Okay, we'll try to get that up in a second.
Thank you.
And we'll come back to you.
Appreciate it.
Oh, hold on. We do have it.
Thank you.
Okay.
Voila. That is it.
Okay.
Okay, the really dark area that looks like a tunnel is just the side of the nucleus that has no sunlight shining on it. So it's completely black. There's basically no light shining on it at all. So you have the nucleus here. You're looking at the back side. You're looking at the back side of a nucleus, and it's black just like this. The whole nucleus is very dark. The white areas of the nucleus are as black as this. There's sunlight shining on one side of it, and so you see an edge that's very bright, and the ejecta are coming out the other side. So if you're looking from that side, here's the back side, the dark side, here's the illuminated edge over here, and the ejecta are coming off this way and spreading out beyond the nucleus. Does that help?
Thank you very much.
That's your pointer if you wanted to show it on your...
Yes, I know it's a pointer,
I'm sorry.
but I was trained not to turn around.
Thank you. We talked to them. Okay, we have a question here back at JPL. Please. Okay, go ahead.
Emily Lakdawala with the Planetary Society. I know that one of the things that you were looking for was what angle the ejecta was coming out, and it was hard for me to tell on the images whether we were seeing something narrow or something very broad. Can you describe what you saw in the images?
Well, the central portion is very high angle, but there also is a second plume angle that is more inclined. But to really figure out what that is, we need to process these images, try to get some stereo or something to create a model of the surface, because we're seeing the shadow, and so it's going to be very much an effect of how that shadow is cast and what the slope away from the impact and what it looks like. So I think it's still preliminary, but at least we know we have an incline, the curtain that is expanding out.
We're going to go to the Washington Post.
Guy Guglielmo of the Washington Post. I guess for Mike or Pete. Mike, you mentioned that the plume is probably going to be there, could be there for weeks.
It could be. They might not be.
Or might not be. If it is, could you speculate a little bit on why it would prolong? Does that mean that there's something that's triggering a continuing reaction down there, and what could that be?
Generally, that would just be the existence of much more volatile material. Once you excavate down deeply, you get more carbon dioxide, i.e. dry ice, more carbon monoxide, irradiated material, any of those. Outgassing for a long time.
Sky and Telescope magazine.
Yes, hi, this is Kelly Beatty. This is for Mr. Gramier or Dr. Ahern. About 2.5 years ago, this project was, as I recall, pretty far over budget and behind schedule. What did you tell the review committees and NASA managers to convince them to go forward, and how close were you to having the mission actually canceled?
I think that should be a question for Andy Dantzler. We were very close to being canceled, I will say that.
How do I answer that? Of course, we do have to watch. We have to watch the money. All Discovery missions, as well as most missions, in science, are competitively selected, and so they're selected on the basis of how much science, essentially how much science per dollar they can do within a certain cost cap. If a project is getting too close to that cost cap, at that point, it's not a question of automatic termination. It's a question of how far along is the project, is there hope of recovery, how much more money would it take, and it gives us a chance to look at the project at that point and say, is this still worth the money? Is it still worth the science? That would be the message that was given to us at the time, a couple of years ago. And we headquarters did decide, of course, as you well know, to proceed with the mission. Some of the cost overrun, by the way, was inflicted on the Deep Impact mission by headquarters as a consequence of the Genesis mishap. Whenever we have success or failure, we look at that and try to incorporate lessons learned into everything that comes after. With Genesis, we wanted to make sure that everything, or post-Genesis, we wanted to make sure that everything that was about to launch or already up in space, and that includes Stardust, could benefit from everything we learned looking at the Genesis failure. That itself cost a few million extra dollars. But again, when you already have a project well on its way into development, the science still looks like it's going to be extraordinary and very useful. At that point, we make the decision whether to go forward or not. And of course, we made a decision to go forward with Deep Impact. And we're, of course, very glad we did.
Okay, we're going to go back here to JPL. KFWB.
Question for Dr. Ahern and Mr. Schultz. I know we've got a lot of inject out there, but the question I've got realistically, when might we see a fairly clear picture of the crater itself? And from that last images that the spacecraft has that was going away, might we have an indication of just how much of an impact we had, how wide, how deep? Or are we talking, we're only guessing for a while?
Yes. I think it's going to be at least a week of careful image processing before we understand whether the feature we have observed really is the crater itself. We certainly know exactly where to look, what images to look in, and we just need to do a number of image enhancement tricks to separate out. The problem is, of course, that there's this bright dust in front of it, and you're looking through that. So basically, we have to learn how to subtract that out of the picture and then see the residual surface of the nucleus and find the crater in that. We may actually find it more easily by using the IR spectrometer and measuring the temperature at different places and looking for the temperature difference at the crater. And that's, a fairly complicated procedure.
Katie Human from the Denver Post. So there's a couple questions. Does that mean it's going to be a week or so before you guys know who won the pool? And how big is that pool now? And then what are the data that you guys are getting back from observatories so far?
Yeah, it probably means that everybody's pool can't be paid off for another week.
And I think we know whose money we're taking.
Yes, we know some losers for sure. The other observatories around the world typically reported the comet brightening by something like a factor of 5 on a time scale of 10 or 15 minutes. We've had reports from Rosetta. They've actually sent a graph that can be released showing us going up by a factor of 5 in half an hour or something like that, and then coming 2/3 of the way back down in the next 5 hours. So this big brightness change. We've had a number of reports of changes in the abundances of the gases that they see. We have some reports of big changes in the thermal emission from the heat, and that's this incandescent flash that Pete talked about. We have reports of changes in that. We don't have quantitative details on that, how hot it got as observed from Earth.
Maybe have one of you guys describe in a little bit more detail that incandescent flash, what that means.
That's you. Sure.
At the moment of impact, you heat materials to extremely high temperatures. Some of that is heated vapor. Some of it is hot melt droplets from dust from within the crater itself. And it's kind of like firing a flash gun. And it's material that is glowing so brightly that without, like I said, without a light, you could actually take your own picture. It's very similar to that. And it tells us a lot about the cratering process.
Hi, Anthony Cabrera with Space.com and Space News. Flyby is going really well and it survived the whole experience. Is it moving away from the comet right now, or is it following in parallel? And how much fuel does it have left in case you decide to send it to pursue other things while it's out there, since it seems to be working so well?
It's not really parallel in the comet. It's continuing on its orbit, which is basically an elliptical orbit, and it's turning back and imaging and then transmitting the data. So it's just continuing to take it on its normal orbit. In answer to your fuel question, I believe it's somewhere around 100 and I want to say 160, but that may be a little high, kilograms of usable fuel that are left. We do not, at this point in time, have any particular plan for an extended mission or a different mission, anything like that. So right now, we're basically starting to come up with, once we get all the data down and finish the look-back imaging, we'll basically do what we call a mothballing of the spacecraft, put it in a sun-safe mode where it'll continue to be positive on energy, but it won't be overly active. Only the critical systems will stay up.
Do we have any other questions here? Okay. We'll go to Pasadena Star News.
Kim Grosh, I'm from the Pasadena Star News. A couple questions. Can you give us any sense of whether this was on the low end of the, well, obviously it's not at the low end with the house-size crater, but are we talking about a stadium-sized crater as we've heard before? And also the model that you showed, Mr. Schultz, is that a best scenario that you ran beforehand? And can you tell us more about the parameters of that, what the composition was for that model?
Sure. Let me answer the last first, because I don't even remember your first question, just because it's... the experiments used for this experiment, regular, ordinary garden perlite. And the idea behind this was to have something very high porosity, very crushable, and very low density. And one of the characteristics for that particular experiment was that in doing these types of experiments, we noticed that it would penetrate deeply and then stuff would come back out. It's kind of like imagining a fireball coming through the atmosphere or Shoemaker-Levy going through the atmosphere. It goes deep and then kapow, it explodes just by the fact that it's been stopped very quickly. So that's why. That's not a complete simulation, though. There were some other simulations that were done to incorporate more volatile-rich, more gas, easily volatilized material, degassed material. And that's what we really have to add. But now we have to go back to the drawing board, do some more complicated scenarios, compare them with theoretical models, and try to get at the answer. And what the devil was your first question?
House size or stadium?
Oh, house, Well, you see, now this is not fair because I'm in the pool too. So I have to be careful not to show any bias. One, two cratering people on here, and you know, I'm sure he's in this game too. So rather than do that, I think I'll just simply say I think it's big. And leave it at that. I don't think it's house size. I think it's bigger than that.
Question here.
I'm sorry, now I got to think of what my question was. I was actually going to ask about the results from the observatory, but this is Glenda Chu from the San Jose Mercury News. But I wanted to ask Peter Schultz also, does this mean that you're going to be going back to Ames and doing further simulations to see if you can match exactly what you saw last night?
Yeah, and in fact, prior to this, I thought, well, we had pretty well covered everything. And now that we see the aftermath, it's going to be a lot more fun to go back in with this as a constraint and do some additional experiments to see if we can better match things like the light curve, the timing, and extrapolation. And so, yeah, we're heading back up to Northern California. The NASA Ames Road Gun Range has been incredibly important to be able to help us guess what we might see and how long it might take, and it's exceeded expectations.
We have another question from New Scientist.
A couple of questions for Pete. You mentioned in the dynamics of the plume that there seemed to be an initial plume, a narrower plume, and then maybe a slight pause, and then a broader plume. Can you talk a little bit about what that might mean in terms of what was happening in that process?
Sure. We've done experiments like this. Some of my graduate students are looking at the light that's coming out of the crater in the laboratory. And we've seen this before. And it happens when the projectile goes into the surface first and releases its energy below the surface. And then it comes out the opening. So it's like a delayed burst, if you will. And that's just the first guess. We have to assume that there's a chance for that to be revised.
So what is the initial plume then versus
the initial plume? Actually, if you looked at that sequence more carefully, you would see there's one more component that's really important. You also see something that simply evolves like an umbrella that's being expanding. And that's actually the leading edge of the initial vapor plume. So that very first flash actually disappears very quickly, and it evolves as we see this hemisphere expand above the impact. And then out of that comes this glowing mass that's between us and the crater, and that then expands. And then that's when we begin to see the shadow cast across the surface that looks like a large column. And then the curtain. The curtain, the conical curtain later on, simply tells us that we have a crater that's expanding like we would expect in loose material.
Okay, we have time for one more question, and we're going to go to the Associated Press.
Alicia Chang from the Associated Press. Based on what you know so far about Comet Temple 1, can you tell us, what are some of the differences or similarities of Temple 1 compared to the other comets that you've studied, and what some of the differences might mean?
Okay. Well, we knew before we went in that the composition you can easily measure from Earth is actually rather similar to that of Welt 2 and Borrelli. Most of the things that are interesting are much harder to measure from Earth, either because the comet's too faint or the materials don't emit light at the right wavelengths to measure them. We know from going to the other comets, the biggest difference is in the topography of the surface. And this includes the large-scale topography, the overall shape. Comet Borrelli, for example, was elongated and had a significant bend in it. We actually, from the early images of Temple 1, that it also did, but now we see that it's actually a very shape, and I can't tell whether there's any bend in it or not. If you look at the images, one end looks rounded like a cylinder, and the top is sort of concave from the looks of it. So there are differences on the large scale. We don't have a shape model yet. We'll have that from one of our co-investigators probably later this week. We know that there are big differences on the small scale topography also. This is the first time we've seen things on the surface that look like impact craters to many of us. There are a few people who think that there were features on Comet Welt 2 that are impact craters, but many other people don't think those are impact craters. So that's another big difference. The only really smooth area we've seen before is this big plateau on Comet Borrelli, really flat, whereas we have a big flat area on Comet Temple 1, that is actually curving around the surface. We don't understand the physics of what produces those flat surfaces in two physically distinct situations. So there are lots of differences from the data we have so far.
Das Geschoss der Sonde Deep Impact einen Krater in den Kometen Tempel 1 riss, seien ihre spirituellen Rechte verletzt worden. Schließlich glaubten die Menschen ja, dass die Himmelskörper über unser Leben bestimmen. Und Kometen seien Vorboten großen Unheils. Weltraumforscher meinen allerdings, mit dem Kometenexperiment der Erkenntnis über die Entstehung der Welt näher gekommen zu sein. Harald Brenner über den Zusammenstoß im All.
Heute Morgen 7:52 Uhr. Mit rund 37.000 Kilometern pro Stunde rast ein kühlschrankgroßes Geschoss auf den Kometen Tempel 1 zu. Mit einer Kamera zeichnet das Projektil aus Kupfer seinen Kamikaze-Flug auf, bevor es beim Einschlag vollständig verdampft. Jubel bei der NASA, zu Recht. Denn zum ersten Mal blicken Menschen in das Innere eines Kometen. Die Mission Deep Impact ist ein Erfolg, ein großer Tag für die Raumfahrt. Wissenschaftler auf der ganzen Welt verfolgen den Einschlag und seine Auswirkungen. Alle großen Teleskope sind auf den Knall im All gerichtet. Die erdgestützten Beobachtungen werden in den nächsten Tagen weitere Analysen ermöglichen. Der wuchtige Treffer hat einen vermutlich Fußballstadion großen Krater hinterlassen und unerwartet viel Material aus dem Kometenkern ins All geschleudert. Die Muttersonde analysiert den Auswurf und davon erhoffen sich Wissenschaftler grundlegende Erkenntnisse über die Entstehung des Sonnensystems vor 4,6 Milliarden Jahren. Man nimmt an, dass sich im Innern von Kometen noch Urmaterie aus jener Zeit befindet, als sich aus Gas und Staub die Planeten geformt haben. Die Auswertung der Deep Impact Daten wird vermutlich Monate bis Jahre dauern, meint ein gut gelaunter Mike Ahern, wissenschaftlicher Leiter der Mission. Vermutlich beschäftigt mich das Ganze, bis ich in Rente gehe. Besonders gespannt sind die Wissenschaftler darauf, ob der Komet auch organische Stoffe enthält. Das könnte bedeuten, dass Kometeneinschläge einst Leben auf die Erde gebracht haben. Als Deep Impact am 12. Januar auf Kometenjagd geht, interessieren sich die Wissenschaftler aber nicht nur für das Innenleben des kosmischen Vagabunden. Sie wollen auch wissen, ob ihre Abwehrstrategien funktionieren. Ein wesentlicher Punkt hat jetzt geklappt. Das Zielobjekt wurde getroffen. Eine Meisterleistung. Einen kleineren Kometen auf Kollisionskurs mit der Erde könnte man auf diese Weise so weit aus der Bahn kippen, dass er die Erde knapp verfehlt. Das konnte bisher nur Hollywood.
Vorgestern hat die NASA-Sonde Deep Impact den Kometen Tempel 1 beschossen. Sie haben es ja sicher mitbekommen. Das Ganze ist kein Krieg der Sterne und der Komet schlägt auch nicht zurück, wie heute die Bild-Zeitung Panik schürt. Das Spannende an diesem Kometen ist die Urmaterie, die in ihm steckt. Die ist nämlich älter als unser Sonnensystem und sie könnte uns viel über dessen Entstehung verraten. Wir haben die neuesten Bilder dieses einmaligen Schauspiels für Sie und wir haben auch schon die ersten Ergebnisse.
4. Juli, 7:52 Uhr. Mit 37.000 Kilometern pro Stunde rast ein kühlschrankgroßes Geschoss aus Kupfer auf den Kometen Tempel 1 zu und steuert sich selbst ins Ziel. Eine Kamera auf dem Projektil zeichnet den Kamikaze-Flug auf, bevor es beim Einschlag verdampft. Jubel bei der NASA. Zum ersten Mal blicken Menschen in das Innere eines Kometen. Deep Impact, so der Name der Mission, ist ein voller Erfolg. Ein großer Tag für die Raumfahrt. Mit Spannung beobachten Astronomen weltweit noch immer die Folgen des Knalls im All. Alle großen Teleskope sind auf Tempel 1 gerichtet. Auch die ESO, die Europäische Südsternwarte in Chile, hat das Bombardement von Tempel 1 mit allen 7 Rohren verfolgt, darunter das größte Teleskop der Welt. Die ESO-Zentrale in Garching steht per Videokonferenz mit den Astronomen vor Ort in Kontakt. Einen Tag nach dem Einschlag wagt man hier erste Analysen.
Der Komet hat eine Kruste,
Allerdings wissen wir nicht, wie dick diese Kruste ist. Das ist eine der Fragestellungen, die ganz wichtig für die Mission waren, herauszufinden, wie dick ist die Kruste eines Kometen. Und offensichtlich ist die Sonde durch diese Kruste durchgebrochen, also sehr dick kann sie nicht sein. Auf der anderen Seite, die Sonde hat so viel Energie mitgebracht, dass es der Explosion von 4,5 Tonnen Sprengstoff entspricht. Also selbst wenn die Kruste einige Meter dick wäre, die Sonde hätte die wahrscheinlich trotzdem durchschlagen. Dann ging es natürlich hinein in diesen inneren schmutzigen Schneeball, gefroren, Wassereis wahrscheinlich, durchsetzt mit Staub, mit Steinchen und so weiter. Und ja, durch den Aufprall hat die Sonde eben so viel Energie freigesetzt, dass ein Teil davon verdampft ist und dann durch das frisch geschlagene Loch in der Kruste nach außen geblasen worden ist.
Auch für die europäische Sonde Rosetta, zurzeit selbst auf Kometenjagd, sind die Ergebnisse der Deep Impact Mission von großer Bedeutung.
Denn das ist jetzt sozusagen zum Anfassen ein Komet und Rosetta soll ja 2014 selber auf einem Kometenkern landen. Oder zumindest eine kleine Landesonde absetzen. Und die Kollegen dort sind natürlich sehr daran interessiert, schon mal im Vorfeld wirklich zu sehen, wie fest zum Beispiel der Boden ist.
Aber was macht Kometen überhaupt so interessant für uns? Kometen sind Zeitzeugen der Entstehung unseres Sonnensystems. Wie die Planeten haben sich Kometen vor 4,6 Milliarden Jahren aus Gasen und Staubpartikeln gebildet und diese Urmaterie befindet sich noch heute in ihrem Kern. Aber wie genau ihre Zusammensetzung aussieht, ist völlig unbekannt. Deshalb sind Astronomen brennend daran interessiert, an dieses Material heranzukommen. Die Vagabunden aus dem All werden auch schmutzige Schneebälle genannt, weil große Teile ihres Kerns aus Eis und Geröll bestehen. In der Nähe der Sonne taut das Eis und der Komet entwickelt einen leuchtenden Schweif aus Gas und Staub. Kometen könnten aber weit mehr enthalten als nur gefrorenes Wasser und Weltraumdreck, zum Beispiel auch organische Stoffe, Grundbausteine des Lebens. Sollte sich das bewahrheiten, ist es durchaus möglich, dass Kometeneinschläge einst Leben auf die Erde gebracht haben.
Dass es organische Moleküle gibt, ist klar. Organisch heißt aber natürlich nur, dass Kohlenstoff beteiligt ist. Das wussten wir, das haben wir jetzt auch wieder gesehen. Und interessant wird die Sache natürlich jetzt erst, wenn eine intensive und detaillierte Auswertung der Daten einsetzt. Was wir momentan bisher machen konnten und was die Kollegen bisher gemacht haben, sind eigentlich nur sehr schnelle Blicke auf die Spektren, Blicke auf die Bilder. Aber es wird Wochen und Monate dauern, bis wirklich die ganze Information aus den Beobachtungen herausgeholt ist.
Als die Rakete mit Deep Impact an Bord am 12. Januar auf Kometenjagd geht, interessieren sich die Wissenschaftler aber nicht nur für das Innenleben des kosmischen Vagabunden. Sie wollen wissen, ob ihre Abwehrstrategien funktionieren könnten, wenn ein Komet die Erde bedroht. Punkt 1 hat geklappt, das Zielobjekt wurde getroffen, eine logistische Meisterleistung, aber es bleiben Fragen.
Wie fest ist ein solcher Kometenkern? Wir hatten bisher keine Ahnung, keine Information darüber. Wir wussten zwar ungefähr, woraus er besteht und auch wie groß Kometenkerne sind, aber wir haben keine Ahnung über die Dichte, das heißt, wie schwer ein Komet eigentlich ist und auch, wie seine mechanischen Eigenschaften sind. Und das könnte durchaus interessant werden, wenn wir mal in die Lage kommen sollten, einen Kometen von dem Absturz auf die Erde abhalten zu müssen. Dann muss man natürlich wissen, wie fest ist er, damit man seine Strategie entsprechend einrichten kann. Ob man jetzt eine Atombombe unmittelbar auf der Oberfläche zündet, dann möchte man gerne wissen, was dann passiert.
Für den 4 auf 14 Kilometer großen Tempel 1 bleibt der Einschlag ohne Folgen. Seine Bahn ändert sich dadurch praktisch nicht. Aber kleinere Himmelskörper auf Kollisionskurs könnte man mit genügend Zeitvorlauf auf diese Art so weit aus der Bahn kippen, dass sie die Erde knapp verfehlen. Deep Impact hat sich allein schon unter diesem Aspekt gelohnt. Denn außer uns selbst sind erdnahe Kometen oder Asteroiden die größte Bedrohung für die Menschheit.